In 1727, Isaac Newton died in his sleep at the age of 84, leaving behind a mystery that would take centuries to unravel. His executors opened the doors to his private chambers, expecting to find notebooks filled with mathematical diagrams and optical experiments. What they discovered instead sent shockwaves through their carefully ordered world. Stacked in wooden chests and scattered across writing desks lay over 5 million words of manuscripts that had nothing to do with physics. Theological treatises arguing that Christianity had been corrupted, alchemical recipes describing the transmutation of base metals, chronological calculations attempting to date the construction of Solomon's temple, prophetic interpretations predicting the end of the world around the year 2060. The executors faced an impossible choice. They could publish these works and reveal that the greatest scientific mind in history had spent the majority of his intellectual energy on pursuits the Enlightenment considered irrational, or they could hide the manuscripts and preserve the myth of Newton as pure rationalist. They chose concealment. For over 200 years, the hidden Newton remained locked away, accessible only to a handful of scholars who could navigate private collections and auction catalogues. The sanitized version presented to the world showed a man who discovered the laws of motion and universal gravitation through mathematical reasoning and careful experimentation. This Newton represented the triumph of scientific method over medieval superstition. He became the patron saint of Enlightenment rationalism, the proof that human reason could penetrate the deepest mysteries of nature without recourse to theology or mysticism. But this Newton never existed. The real Isaac Newton occupied a radically different intellectual universe, one where natural philosophy, biblical exegesis, and alchemical investigation formed a unified project, aimed at recovering ancient wisdom and revealing divine truth. He did not separate his physics from his theology or his chemistry from his study of prophecy. These were not compartmentalized interests, but aspects of a single comprehensive vision. Understanding this vision requires abandoning modern disciplinary boundaries and entering a world where the mechanical operation of the solar system and the corruption of Christian doctrine in the 4th century were intimately connected problems requiring similar methods of investigation. Newton believed that God had revealed fundamental truths to Noah and the patriarchs before Moses. This original religion consisted of pure monotheism and 2 simple moral commands. Love God with complete devotion and love your neighbour as yourself. Ancient sages in Egypt, Babylon and Greece preserved fragments of this wisdom, encoding it in temple architecture, mathematical philosophy, and mystery religions. But over centuries, priests corrupted the original revelations, transforming pure monotheism into elaborate polytheistic systems, while retaining distorted elements of truth. Pythagoras learned authentic wisdom during his travels and transmitted it to disciples through symbolic teaching. His mathematical philosophy and heliocentric cosmology represented genuine knowledge of natural and divine things. Similarly, the original Christians worshipped one God the Father and honoured Jesus as his appointed Messiah, not as a co-equal divine person. The elaborate Trinitarian metaphysics emerged from Greek philosophical influence corrupting Hebrew monotheism, imposed through political manoeuvring and textual manipulation after the Council of Nicaea in 325. Newton's massive theological manuscripts detailed this alleged historical corruption with meticulous scholarship. He compared textual variants in ancient biblical manuscripts, noting discrepancies in later editions. The famous Johannine comma in 1 John, which appeared to support Trinitarian doctrine, was a late interpolation absent from the earlier sources. He analysed the writings of early church fathers, tracing how theological formulations evolved over the first 4 centuries of Christianity. He studied the proceedings of church councils, documenting the political pressures and personal rivalries that shaped doctrinal decisions. This was not amateur speculation, but rigorous textual criticism, applying empirical methods to sacred texts. Newton approached Scripture as he approached nature, as a source of data requiring careful analysis to separate authentic information from corrupting additions. His conclusion was heretical by any orthodox standard. The doctrine of the Trinity represented a catastrophic distortion of Christianity, transforming simple monotheistic truth into philosophically incoherent metaphysics. God is absolutely one, not three persons sharing one substance. Christ was the Son of God and the Messiah, but not co-equal or co-eternal with the Father. This made Newton an Arian, following the ancient theologian Arius, whose views the Council of Nicaea had condemned. Only the Father is the supreme God, existing from eternity and possessing ultimate divine authority. The Son and Holy Spirit are subordinate beings, creatures of the Father rather than eternal aspects of a triune deity. These convictions placed Newton in mortal danger throughout his adult life. In 17th century England, denying the Trinity constituted formal heresy, punishable by loss of university position, imprisonment, or worse. Cambridge professors were required to take holy orders in the Church of England, which meant swearing to articles of faith Newton believed fundamentally false. In 1675, he faced a crisis when the time came for his ordination. He could not in conscience affirm doctrines he considered corrupt additions to original Christianity. Through the intervention of Isaac Barrow, his patron and predecessor as Lucasian professor, Newton obtained special dispensation. The statute requiring ordination was changed specifically to exempt the Lucasian chair. This narrow escape convinced Newton that his theological views must remain absolutely private. He adopted what scholars call Nicodemism, concealing heretical beliefs through outward conformity. He attended church services regularly, received communion, and subscribed publicly to Anglican articles when accepting government positions. But these were strategic concessions protecting his ability to continue his work. In private correspondence with trusted friends like John Locke, Newton hinted at his views, but never published the manuscripts that would have revealed the full extent of his heterodoxy. The fear of exposure haunted him. When he sent Locke a treatise disputing the scriptural basis for the Trinity, he immediately regretted it and demanded the manuscript back, fearful that it might somehow become public. The alchemical manuscripts presented a different kind of challenge to Newton's executors. By the early 18th century, alchemy was becoming intellectually suspect, associated with fraudulent claims of transmutation and mystical obscurantism. Yet Newton had devoted decades to alchemical research, filling over 1 million words with copied recipes, experimental records, and theoretical speculations. He built a laboratory adjacent to his chambers at Trinity College and conducted dangerous experiments involving mercury, antimony, and other toxic substances. He systematically transcribed alchemical text by hand, a laborious process suggesting he considered them worthy of intense study. He developed theories about active principles in matter that could explain chemical affinities and transformations beyond what mechanical philosophy could account for. For Newton, alchemy was legitimate natural philosophy, an empirical investigation of matter's properties and the forces operating at microscopic scales. The boundary between chemistry and alchemy did not exist in his time as it would later. Both investigated how substances combined, separated, and transformed through observable processes. Alchemy pursued more speculative goals like transmutation of base metals into gold, but it also encompassed metallurgy, medicine, dye production, and other practical chemical arts. Newton approached alchemical substances with the same empirical rigour he applied to prisms and lenses. He conducted controlled experiments, varied conditions systematically, and kept detailed records of results. The difference lay not in method, but in the theoretical framework. Where mechanical philosophers like Descartes tried to explain all phenomena through size, shape, and motion of matter alone, Newton suspected that chemical phenomena revealed active principles beyond purely mechanical interactions. These active principles might involve short-range attractive and repulsive forces between particles, analogous to gravity but operating at different scales. Chemical affinity, where certain substances preferentially combine while others remain inert, suggested forces guiding selective combinations. Why does acid dissolve some metals but not others, despite similar mechanical properties? Mechanical collision cannot explain such selectivity. Newton believed that understanding these microscopic forces might unlock deeper truths about matter's nature and the hierarchies of power operating throughout creation. The philosopher's stone represented matter in its most active and perfected state, embodying maximum virtue or power. Transmutation might be possible by transferring these active principles to base metals, fundamentally altering their essential nature through a natural process that mechanical philosophy could not explain. This was not magic, but natural philosophy extended into domains where mechanical explanations failed. The alchemical investigation complemented mathematical physics by exploring aspects of divine action in matter that equations could not capture. Both aimed at revealing God's ways of working in creation, using different methods appropriate to different scales and phenomena. The prophetic manuscripts revealed yet another dimension of Newton's intellectual project. He studied the books of Daniel and Revelation as encoded information about God's plan for human history. These texts contained encrypted timelines showing the rise and fall of kingdoms, the corruption of true religion, and its eventual restoration before the end times. Newton developed elaborate interpretive principles for matching prophetic symbols to historical realities. Beasts represented kingdoms, horns represented rulers. Time periods could be decoded using the day-year principle, where each prophetic day corresponded to an actual year. Applying these methods, he calculated that the corruption of Christianity began when Charlemagne was crowned Holy Roman Emperor in the year 800, establishing the political religious system that would dominate Europe for over a millennium. The restoration of true religion would not occur until approximately 2060. Though Newton cautioned that this was a general time frame rather than a precise prediction. He saw himself living during the long prophesied apostasy, a period when corrupted Christianity held sway, but authentic truth remained accessible to those willing to study ancient sources critically. His natural philosophical work and his theological research both contributed to preparing for the eventual restoration by recovering wisdom that had been lost or distorted over centuries of decline. Understanding why Newton's executors concealed these manuscripts requires recognizing the threat they posed to his carefully constructed public image. The Principia Mathematica and the Optics had established Newton as the supreme exemplar of the new scientific method, a man who derived conclusions from phenomena through mathematical reasoning and experimental verification. Publishing theological writings denying the Trinity would brand him a heretic, potentially invalidating his scientific achievements in the eyes of orthodox believers. Publishing alchemical manuscripts would suggest he wasted time on irrational pursuits when he could have made further contributions to legitimate science. Publishing prophetic calculations would make him appear as a religious enthusiast rather than a sober natural philosopher. The executors believed they were protecting Newton's reputation and preserving his contributions to human knowledge by hiding the aspects of his work that did not fit the emerging Enlightenment narrative. They could not have known that this concealment would distort understanding of Newton for generations, creating a mythological figure who bore little resemblance to the historical person. The sanitized Newton became a weapon in philosophical and religious debates. Enlightenment thinkers invoked him as proof that reason could operate independently of revelation. Deists cited him to argue for a God who created natural laws and then withdrew from active intervention. Materialists used his mechanical explanations to eliminate purpose and design from nature. Each group selectively appropriated elements of Newton's public work while ignoring or remaining ignorant of the theological and alchemical foundations that actually motivated his research. Only in the 20th century did the hidden manuscripts begin emerging into public view through auction sales and scholarly investigation. When they finally became available for study, they revolutionized Newton's scholarship by revealing dimensions completely absent from standard historical accounts. The rational, mechanistic Newton of Enlightenment mythology gave way to a far more complex figure who simultaneously pursued multiple paths toward understanding nature and divinity. He was indeed the founder of mathematical physics, but he was also an obsessive biblical scholar who questioned core Christian doctrines, an alchemical experimenter searching for active principles in matter, and a chronological investigator attempting to reconstruct ancient history through astronomical calculation. These were not separate compartments of his life, but aspects of a unified vision aimed at recovering the Prisca Sapientia, the ancient wisdom about natural and divine things that had been corrupted over centuries of decline. Modern physics confirmed some alchemical intuitions while rejecting others completely. Transmutation became possible through nuclear reactions, though not via the philosopher's stone. Chemical reactions do involve forces between atoms, though not purely mechanical collisions. Newton's supposition that active principles govern matter contained genuine insight, even though his specific theoretical framework proved incorrect. His experimental technique influenced later chemistry, despite the ultimate failure of his alchemical theories. Careful, systematic experimentation with detailed record-keeping became standard practice in chemical investigation, separating his valid methodology from his invalid theories. The theological manuscripts remain more difficult to assess because they address questions beyond empirical verification. Was Christianity corrupted in the 4th century as Newton believed? Did Trinitarian doctrine represent Greek philosophical influence distorting Hebrew monotheism? These claims involve historical and theological judgments where evidence admits multiple interpretations. What remains clear is that Newton invested enormous intellectual energy in these investigations, treating them as seriously as his mathematical work. The emotional and spiritual stakes were perhaps even higher in theology than in physics, since they concerned his soul's salvation and his relationship with God. He could not separate his natural philosophy from his theological convictions, because both aimed at the same ultimate goal: understanding and revealing divine truth. The God who created the mathematical laws governing planetary motion was the same God who revealed true religion to ancient patriarchs, and who would eventually restore corrupted Christianity to its original purity. Physics and theology were not separate enterprises but different approaches to comprehending the divine nature and how God acts in the world. This unified vision, hidden for 2 centuries after Newton's death, is essential for grasping what drove one of history's most powerful intellects to revolutionize multiple fields while maintaining absolute secrecy about the foundations of his thought. Isaac Newton entered Cambridge University in 1661 during a period of extraordinary intellectual upheaval across Europe. The Aristotelian philosophy that had dominated universities for centuries was collapsing under assault from multiple directions. Cartesianism spread rapidly, offering a mechanistic vision of nature that promised to eliminate occult qualities and mysterious forces. Experimental philosophy emerged in England through the newly founded Royal Society, emphasizing observation and controlled experimentation over textual authority. These competing approaches created fierce debates about fundamental questions. What is the nature of matter? How does motion occur? What role does mathematics play in understanding nature? Can we achieve certain knowledge about the physical world, and if so, through what methods? The young Newton absorbed these controversies with intense focus, reading widely in both ancient and modern sources. He studied Aristotle and the scholastic commentators who had interpreted him for medieval universities. He read Descartes' Principles of Philosophy and Meditations, absorbing the Cartesian method of systematic doubt and mechanical explanation. He encountered the experimental work of Robert Boyle and Robert Hooke, learning techniques for investigating nature through controlled manipulation. From this intellectual ferment, Newton began developing his own distinctive approach, one that would ultimately transform natural philosophy more profoundly than any single thinker since Aristotle himself. René Descartes had argued that physical reality consists entirely of matter in motion, with matter defined as extension in 3 dimensions. For Descartes, saying something is material and saying it occupies space meant exactly the same thing. This identification of matter with extension had radical consequences. If matter just is extension, then space cannot exist independently of the bodies filling it. Empty space would be extension without extension, a logical contradiction. Therefore, the universe must be completely full, with no void or vacuum anywhere. All motion occurs through bodies pushing adjacent bodies in vast whirlpools called vortices. These vortices circulate around the sun and planets, carrying celestial bodies along like leaves in a stream. Planetary motion results from being caught in the solar vortex, with each planet's distance from the sun determined by the balance between centrifugal tendency and vortical pressure pushing inward. This mechanical system appealed to many natural philosophers because it seemed to eliminate action at a distance, the idea that one body could affect another across empty space without any intervening medium. Everything happened through direct contact between bodies, making causation mechanically intelligible. But Descartes' system troubled those who saw it, reducing God's role to merely starting the cosmic machine, leaving no room for ongoing divine action in nature. Newton read Descartes carefully, but rejected almost every major doctrine of Cartesian philosophy. This rejection was not casual disagreement, but fundamental opposition extending to the foundations of metaphysics. Where Descartes identified matter with extension, Newton insisted that space exists independently of any material bodies. Space is real, existing in its own right whether or not any matter occupies it. This absolute space became central to Newton's entire system, providing the stage on which all physical processes unfold. But what exactly is absolute space? Newton explained it as distinct from relative space, which we experience through the positions of observable bodies. Relative space consists of the spatial relationships between objects, the distances and directions that connect them. Absolute space, by contrast, exists prior to and independent of any such relationships. It is not defined by relations between objects, but provides the framework within which those relations occur. Absolute space cannot move or change, remaining eternally uniform and immovable. It extends infinitely in all directions, forming a kind of container within which the entire material universe exists. This was philosophically radical because it made space something like a substance, an entity with its own existence, rather than merely a property of material things or a set of relations between them. Newton went even further by identifying absolute space with God's omnipresence. In the general scholium appended to the second edition of the Principia, he wrote that God exists always and everywhere. By existing everywhere, God literally constitutes space itself through his eternal, ubiquitous presence. Space is not a container independent of God, but rather the manifestation of divine presence pervading all creation. This identification shocked many contemporaries who believed God exists outside or beyond the physical world. For Newton, claiming that God exists outside space was tantamount to claiming God does not exist at all. Every entity must be related to space somehow, otherwise it simply has no reality. This applies to minds, souls, and God himself, just as much as to physical bodies. Spirits are not spaceless, but occupy space differently than matter does. God, being omnipresent, occupies all of space simultaneously and necessarily. The infinity of space reflects God's infinite nature. The uniformity of space reflects God's immutability. Absolute space is thus quasi-divine, more an attribute of divinity than a feature of physical reality. This theological dimension was inseparable from Newton's physics, despite later sanitization that presented his mechanics as purely secular science. Descartes had also argued that motion is purely relative, existing only with respect to surrounding bodies. A body moves when it changes position relative to adjacent bodies taken as reference frame. There is no fact about whether something is really moving or really at rest, only whether it moves relative to some chosen reference. This made motion entirely a matter of perspective with no absolute standard. Newton insisted this view makes physics impossible by eliminating any stable foundation for laws of motion. If all motion is relative, then the same body could be simultaneously at rest in one reference frame and moving in another, with no way to say which description is correct. The laws of motion require distinguishing real motion from merely apparent motion, real forces from fictitious forces. Without absolute space and absolute motion, we cannot formulate dynamical laws at all. Newton's famous bucket experiment attempted to demonstrate that true rotation can be distinguished from merely apparent rotation. When you spin a bucket of water, the water initially remains flat while the bucket rotates around it. Then friction gradually causes the water to rotate with the bucket, and as it does, the surface becomes concave, rising up the sides. Eventually the water and bucket rotate together with no relative motion between them, yet the water surface remains concave. This concavity, Newton argued, reveals genuine rotation relative to space itself rather than relative to surrounding bodies. The water's behaviour depends on its absolute rotation, not its motion relative to the bucket or any other material reference frame. However, Newton faced a profound problem he never fully resolved. Absolute space and time cannot be directly observed or measured in any experiment. We always perceive only relative motions and relative positions of observable bodies. No measurement gives us direct empirical access to the absolute magnitudes Newton's system requires. He openly acknowledged this difficulty, noting that we lack direct empirical access to absolute quantities. His solution was to treat absolute space as a conceptual foundation that allows physics to proceed. We use theory-mediated measurements to infer properties we cannot observe directly. Forces acting on bodies provide clues for distinguishing real from apparent accelerations. True motion does not arise or change without forces acting on the body itself. This created tensions that subsequent philosophers spent centuries trying to resolve. Newton claimed to follow experimental philosophy and derive conclusions solely from phenomena. Yet his fundamental framework relied on metaphysical entities beyond any possible observation. Critics accused him of smuggling in precisely the kind of speculation he claimed to reject. The dispute with Gottfried Leibniz brought these problems into public view. Leibniz developed relationism, the view that space is nothing but relations between physical objects. Time, likewise, is nothing but the succession of events involving those objects. For Leibniz, absolute space was an incoherent notion violating the principle of sufficient reason. If space exists absolutely, why would God place the material universe at one location in that space rather than another? There could be no sufficient reason for choosing one position over another in an undifferentiated absolute space. Yet God does nothing without sufficient reason. Therefore, absolute space cannot exist. Samuel Clerk defended Newton in the famous Leibniz-Clerk correspondence of 1715 and 1716. The debate ranged across physics, metaphysics, and theology, with neither side conceding their positions. Both recognized that fundamental questions about God's relation to creation were at stake. This was not merely abstract philosophy, but touched on the deepest issues about divine action. Newton believed God actively intervenes in the universe, maintaining its order and structure through continuous providential governance. He rejected Leibniz's claim that God created a perfect world requiring no subsequent divine intervention. For Newton, signs of divine management appeared everywhere in phenomena requiring ongoing providential action. The stability of the solar system, and the arrangement of planetary orbits suggested constant intelligent direction rather than self-maintaining mechanical equilibrium. Comets travelling through the system might gradually disturb planetary motions, requiring periodic divine corrections to prevent accumulated perturbations from destroying the system's regularity. This was not an admission of design flaws, but recognition that creation manifests continuous divine care rather than autonomous mechanical operation. The theological dimension was inseparable from natural philosophy, despite subsequent purification that tried to separate them. The general scholium concluded with Newton's statement that discussing God from phenomena constitutes the true business of natural philosophy. This was not an afterthought, but expressed his foundational conviction about the unity of physics and theology. He practiced theology when calculating planetary orbits, just as much as when studying biblical prophecies. Both activities aimed at revealing God's nature and ways of acting in the world. His absolute space thus served multiple functions simultaneously. Physically, it provided the framework for formulating laws of motion and distinguishing inertial from non-inertial reference frames. Metaphysically, it solved the problem of motion's reality by providing an absolute standard. Theologically, it manifested God's omnipresence and allowed for direct divine action throughout creation. These functions were not separable in Newton's thinking. The physics required the metaphysics, and the metaphysics had theological implications that shaped how he understood natural processes. Modern physics eventually rejected absolute space, while retaining aspects of Newton's insights in transformed ways. Einstein's special relativity showed that no absolute simultaneity exists, making absolute time incoherent. Different observers moving relative to each other experience different time orderings of distant events. General relativity made space-time itself dynamical, curved by matter and energy rather than existing as a fixed background. Yet something like Newton's distinction between inertial and non-inertial motion survived these revolutions. General relativity distinguishes free-fall trajectories from accelerated motions, providing an absolute structure, though not Newton's absolute space. The philosophical problems Newton identified remain relevant even after relativity. How do laws of nature relate to the structure of space and time? Can we ground physical laws in geometrical or topological features of space-time? What metaphysical commitments does successful physics require? These questions continue generating debate among philosophers of physics. Newton's absolute space proved incorrect in its specific form, but raised issues that cannot be dismissed simply by rejecting his particular solution. The need for some kind of absolute structure to formulate dynamical laws remains pressing even in contemporary physics. Quantum field theory, the framework underlying modern particle physics, requires background space-time structure to define quantum states and evolution. Some approaches to quantum gravity attempt to make space-time itself emergent from more fundamental entities, but then face the challenge of recovering the approximately absolute structure we observe at large scales. Newton's insistence that physics needs more than just relative positions and motions captures something deep about how we understand natural processes, even if absolute space itself does not exist. His identification of space with divine presence reflected theological commitments modern physics does not share. Yet it showed profound awareness that space's nature raises fundamental metaphysical questions rather than being merely an empirical matter. The theological framework may have been mistaken, but the recognition that space's ontological status requires philosophical argument rather than simply following from observation remains valid. The concept of absolute time raised similar issues. Newton argued that true time flows uniformly, regardless of any particular motions or changes occurring in the material world. This absolute time provides the measure for all duration, whether of physical processes, mental events, or divine eternity. Like absolute space, absolute time cannot be directly observed. We measure time using periodic processes like planetary motions or pendulum swings, but these give us only apparent time. True time lies behind these measurements as an absolute standard that particular clocks approximate with greater or lesser accuracy. Why did Newton need absolute time? For the same reason he needed absolute space to formulate laws of motion precisely. His second law states that force equals mass times acceleration, but acceleration is rate of change of velocity, which is rate of change of position. These rates of change must be taken with respect to some time parameter. If time is merely relative, defined by the motions we use to measure it, then the second law becomes circular. We would be defining forces in terms of accelerations measured by clocks, whose motion is itself supposed to be explained by forces. Absolute time breaks this circle by providing an independent parameter against which all motions and changes can be measured. The flow of absolute time remains uniform whether anything happens or not, providing the ultimate metronome for all physical processes. The publication of Newton's first major scientific paper in 1672 ignited controversies that would shape his entire approach to natural philosophy. He sent the Royal Society a letter describing experiments with prisms that revealed white light's composite nature. Newton believed his experimental demonstrations provided certain proof, not mere hypothesis. The paper claimed that conclusions followed geometrically and inevitably from observed phenomena, establishing facts rather than proposing speculations. Robert Hooke immediately attacked the paper with numerous objections and alternative explanations. Hooke was England's leading authority on optics, and resented this challenge from a younger, relatively unknown Cambridge scholar. He argued that Newton's theory rested on the assumption that light consists of particles or corpuscles. Since Hooke believed light propagates as waves, Newton's entire theoretical framework must be mistaken. This criticism enraged Newton because he considered it a complete misreading of his argument. Newton insisted his theory of colour did not depend on any hypothesis about light's ultimate nature. Whether light consists of particles or waves, the experimental facts about refrangibility remain unchanged. The theory represented demonstrated conclusions, not speculative hypotheses about hidden mechanisms. Christian Huygens also criticised Newton's conclusions, though more temperately than Hooke. Huygens had developed a sophisticated wave theory of light, based on earlier ideas, showing that treating light as waves propagating through an ether could explain reflection and refraction. His principle stated that each point on a wavefront generates new waves spreading spherically outward. The controversies about whether light consists of particles or waves would continue for over 2 centuries, with Newton developing and defending corpuscular theory, while Hooke and Huygens championed wave theories. Each side could convincingly explain some phenomena while struggling with others. Corpuscular theory naturally accounted for rectilinear propagation and sharp shadows. Newton argued that if light were waves, it should bend around obstacles the way sound does. We hear sounds from around corners, but do not see light sources blocked by obstacles. This suggested light travels in straight lines like particles rather than spreading in all directions like waves. The attacks left Newton feeling deeply misunderstood, and this experience shaped his lifelong aversion to public debate. He became convinced that most natural philosophers lacked the mathematical sophistication and experimental care to evaluate his work properly. He would spend decades refining his ideas before publishing them, and even then only under pressure from colleagues who recognized their importance. These conflicts forced Newton to articulate clear principles about how natural philosophy should proceed. He needed to distinguish what he considered rigorous knowledge from mere speculation or hypothesis. This led him to develop what scholars now call his epistemic triad, a 3-part classification of propositions in natural philosophy. First come theories, which are certain and experimentally established. These represent demonstrated knowledge derived rigorously from phenomena. Second come hypotheses, which remain speculative and unproven. These might be plausible or useful for investigation, but do not constitute established truth. Third come queries, propositions that are uncertain but provide proper means for establishing theoretical certainty. Queries could play a heuristic role in research without claiming to be proven facts derived from observation. A hypothesis might serve as a provisional assumption for reasoning from phenomena to conclusions, but Newton refused to present hypotheses as demonstrated truths. This framework changed substantially between the first edition of the Principia in 1687 and later versions. The first edition's third book contained 9 propositions labelled as hypotheses. By the second edition in 1713, Newton had restructured everything, leaving only 2 hypotheses while renaming the rest as rules of reasoning or phenomena depending on their logical function. The 4 rules of reasoning became Newton's most explicit methodological statement. Rule 1 requires admitting only those causes that are both true and sufficient to explain phenomena. This is Newton's version of Occam's razor, his principle of parsimony in theory construction. More is useless when less serves as adequate explanation. We should not multiply entities or causes beyond what phenomena actually require. Rule 2 states that similar natural effects must be assigned the same causes as far as possible. The falling of stones in Europe and America has the same cause. Respiration in humans and animals has the same cause. This rule allows extending conclusions from observed cases to unobserved similar cases, providing a bridge from particular experiments to universal laws of nature. Without such a principle, we can never generalize beyond the specific instances we have actually examined. Rule 3 asserts that qualities found in all bodies accessible to experimental investigation are universal properties of all matter. If every body we can test proves impenetrable, we conclude that all bodies possess impenetrability everywhere. This rule justified treating gravity as a universal property of all matter throughout the cosmos. Newton had investigated only terrestrial objects and celestial bodies visible from Earth, yet he claimed gravity operates universally in all matter at all locations. Rule 3 provided methodological warrant for this vast extrapolation from limited evidence. Rule 4 became the most controversial and philosophically rich of Newton's methodological principles. Propositions gathered from phenomena by induction should be considered exactly or very nearly true until contrary phenomena appear that modify them or specify exceptions. This rule explicitly prioritizes propositions over hypotheses and experiment over speculation. The key idea is that inductive propositions maintain provisional certainty despite potential revisability. Newton acknowledged that perfect certainty is unattainable in natural philosophy. Nevertheless, he insisted we can achieve knowledge sufficient for practical and theoretical purposes. We must not allow hypothetical possibilities to undermine conclusions properly drawn from phenomena. The rule protected hard-won empirical knowledge from being dissolved by speculative doubts. If phenomena consistently support a conclusion and no contrary phenomena have appeared, that conclusion deserves acceptance as true even though future observations might someday require revision. This represented a mature epistemology, recognizing both the fallibility and the substantial reliability of well-conducted empirical investigation. Newton was navigating between the extremes of rationalist overconfidence and skeptical paralysis. Pure rationalism claimed to derive necessary truths through reason alone, achieving absolute certainty. Pure skepticism questioned whether we can know anything beyond immediate sensory experience. Newton's position acknowledged uncertainty, while defending the legitimacy of inductive generalization from careful observation. By the second edition, Newton added the general scholium containing his most famous methodological declaration. After explaining that he could not deduce the cause of gravity from phenomena, he wrote the Latin phrase hypotheses non fingo. This phrase means either I do not feign hypotheses or I frame no hypotheses, with the ambiguity generating centuries of scholarly debate. Newton clarified that whatever is not deduced from phenomena must be called hypothesis. Such hypotheses have no place in experimental philosophy, whether they be metaphysical, physical, mechanical, or based on occult qualities. In experimental philosophy, particular propositions are inferred from phenomena and then generalized by induction. This was Newton's mature statement distinguishing his method from rationalist system building. He would not construct comprehensive explanatory schemes without solid empirical foundation at every step. The phrase targeted primarily Descartes and Leibniz, who had proposed mechanical explanations for gravity. Leibniz introduced vortices or whirlpools as hypothetical fluids surrounding planets to account for orbital motion. Newton considered this feigning hypothesis, inventing unobservable mechanisms not required by observational evidence. He had established gravity's mathematical law and shown that it suffices for explaining celestial phenomena. The question of how gravity operates, or what mechanism transmits the force across empty space, remained open for future investigation. Critics charged that Newton himself feigned hypothesis by postulating action at a distance. How could one body affect another across empty space without any intervening medium or mechanism? This seemed to reintroduce occult qualities that mechanical philosophy had supposedly eliminated from natural explanation. Gravity, acting across a vacuum, appeared to violate the principle that matter affects matter only through direct contact. Leibniz and continental thinkers found it philosophically repugnant, despite the theory's mathematical success and predictive accuracy. Newton's response was that he had demonstrated gravity exists and acts according to precise mathematical laws derived from careful observation. Whether gravity operates through unknown mechanisms or directly across space remained an open question requiring further investigation. He privately believed some mechanism might exist, and even speculated about ethers at various times in his career. But he refused to publish such speculations as demonstrated truths derived from phenomena. Publishing them would violate his own methodological principles by presenting unproven hypotheses as established conclusions. This methodological stance represented a profound shift in what counted as legitimate scientific explanation. Previous natural philosophy demanded identifying causes and mechanisms underlying all observed effects. Newton argued that mathematical description of how phenomena behave could constitute adequate knowledge even without knowing why. We need not know why gravity follows an inverse square law to use that law successfully for prediction and explanation. The distinction between knowing that and knowing why became central to subsequent philosophy of science. Newton showed that precise mathematical laws describing observable regularities constitute real scientific achievement worthy of the name knowledge. Demanding mechanical explanations or underlying causes might be premature before sufficient phenomena are examined thoroughly. Better to establish secure mathematical descriptions than to multiply unsupported hypothetical mechanisms that may prove incorrect. Yet Newton never abandoned the search for deeper explanations or underlying physical causes. His optics concluded with dozens of queries posing questions about the nature of light, matter, and force. These queries were clearly not demonstrated conclusions, but speculative proposals for future investigation. They suggested subtle fluids, active principles, and mechanisms that might explain observed phenomena once sufficient evidence accumulated. The methodology balanced two opposing dangers Newton navigated throughout his career. Pure empiricism risked drowning in observations without achieving general understanding or theoretical power. Pure rationalism risked constructing elegant systems detached from observational constraints and experimental test. Newton's synthesis demanded mathematical rigor and deductive reasoning, while insisting these be disciplined by empirical phenomena at every stage. His approach required extraordinary mathematical invention to handle the complexities of real observations. The Principia uses sophisticated geometric methods to derive conclusions from idealized situations, then shows how to account for deviations between ideal theory and actual measurements. Successive approximations increase model complexity to capture phenomena with greater accuracy. This iterative method of refinement became standard practice in mathematical physics. You start with simplified models capturing essential features, while deliberately ignoring complicating factors. After securing basic understanding, you systematically add complications and correct for disturbing influences. Newton demonstrated this approach throughout the Principia's development of celestial mechanics. Book 1 derived general theorems about motion under central forces using pure geometry. Book 2 analysed motion in resisting media and systematically demolished Cartesian vortex theories. Book 3 applied the mathematical machinery to our actual solar system, deriving planetary motions from empirical data. The methodology also incorporated what we would now call error analysis and uncertainty quantification. Newton explicitly acknowledged that measurements contain errors and observations capture only approximations. He developed techniques for extracting reliable conclusions from imperfect data, recognizing that different observations might give slightly different values for the same quantity. This recognition that certainty comes in degrees marked a mature understanding of empirical science rarely achieved before Newton. Most philosophers had sought either absolute certainty or admitted complete skepticism about the external world. Newton carved out middle ground where well-conducted investigation yields knowledge that is reliable without being infallible, certain enough for practical application while remaining open to refinement. Newton's rules of reasoning influenced methodology for 2 centuries after his death. They shaped how scientists justified inductive inferences and extended conclusions beyond observed cases. David Hume's skeptical analysis of causation and induction took Newton's approach as its explicit target. Hume argued that we cannot rationally justify induction, because any argument for induction's reliability would itself rely on inductive reasoning, creating vicious circularity. We observe constant conjunctions of events and form expectations, but we never perceive necessary connections between causes and effects. The idea of causal power is psychological projection rather than empirical discovery. This skeptical argument threatened to undermine Newton's entire framework philosophically. If induction lacks rational foundation, then Newton's conclusions from phenomena become unjustified despite their practical success. Immanuel Kant developed transcendental philosophy, partly to explain how Newtonian science achieves synthetic knowledge about nature, despite the problems Hume identified. Kant argued that space and time are not features of things in themselves, but forms of sensuous intuition, structuring all possible experience. Similarly, causation is not discovered empirically, but imposed by our understanding as a necessary condition for objective experience. This explained both the success of Newtonian physics and the limits of what natural science can reveal about ultimate reality. The hypotheses non-fingo declaration became a rallying cry for empiricist philosophy of science throughout the 19th century. Positivists invoked Newton as their patron saint, championing rejection of metaphysical speculation in favour of mathematical description of observable phenomena. This was deeply ironic given Newton's private commitment to metaphysics, theology and alchemy. The sanitised Newton of Enlightenment mythology bore little resemblance to the actual historical figure who believed physics and theology formed a unified project aimed at revealing divine action in creation. The real Newton feigned plenty of hypotheses in private manuscripts, while publicly maintaining that experimental philosophy must avoid speculation. His methodological principles described an ideal he pursued rather than his actual practice, which included extensive theorizing about unobservable entities and processes. Isaac Newton was a heretic who concealed his true beliefs throughout his entire adult life, with the discipline of a secret agent operating in hostile territory. He rejected the doctrine of the Trinity, the central dogma that distinguished Orthodox Christianity from ancient heresies condemned by church councils. He believed institutional Christianity had undergone catastrophic corruption during the 4th century following the Council of Nicaea in 325. This corruption transformed the simple monotheism taught by Christ and the Apostles into elaborate metaphysical formulations borrowed from Greek philosophy. Newton's theological investigations consumed as much intellectual energy as his mathematical work, perhaps more. He wrote treatises on biblical prophecy totaling over 3 million words, far exceeding his output on physics and mathematics combined. He studied ancient manuscripts with philological rigour, comparing textual variants and tracing the evolution of Christian doctrine through patristic sources. His textual scholarship applied critical methods to sacred texts with the same empirical care he brought to optical experiments. The manuscript he sent to John Locke disputing the Trinity's scriptural basis was never published during his lifetime. Newton feared the consequences of revealing views that constituted formal heresy under English law. In 17th century England, denying the Trinity could destroy careers and potentially endanger lives. The Act of Uniformity required subscription to the 39 Articles of the Church of England, which explicitly affirmed Trinitarian doctrine. Cambridge professors were expected to take holy orders, meaning they must swear to articles of faith Newton believed fundamentally false. He faced a crisis in 1675 when the time came for his ordination as required by university statute. He could not in conscience affirm that God exists in 3 persons of one substance, that the Son is co-equal and co-eternal with the Father, or that the Holy Spirit proceeds from both Father and Son. These formulations struck him as logical contradictions dressed in theological language, human inventions corrupting simple biblical truth. Through the intervention of Isaac Barrow, his patron and predecessor as Lucasian Professor of Mathematics, Newton obtained special royal dispensation. King Charles II issued a decree permanently exempting the Lucasian chair from the ordination requirement. This narrow escape convinced Newton that his theological views must remain absolutely secret. He adopted a strategy scholars call Nicodemism, after Nicodemus, who came to Jesus by night to avoid public association. Newton attended church services regularly and received communion at appropriate times. He subscribed publicly to Anglican articles when accepting the position of Master of the Royal Mint, and later when elected to Parliament representing Cambridge University. But these were strategic, performances protecting his ability to continue his work rather than expressions of genuine belief. In private correspondence with trusted friends, Newton hinted at his heterodox views while remaining cautious about full disclosure. When he sent Locke the anti-Trinitarian treatise, he immediately regretted the decision and demanded its return, terrified it might somehow become public. Even with someone as philosophically sympathetic as Locke, Newton could not risk complete openness about convictions that branded him heretical. The psychological burden of maintaining this double life for decades must have been immense. Newton lived constantly aware that discovery would mean professional ruin and public disgrace. His natural tendency towards secrecy and withdrawal from controversy intensified under this pressure. He revealed his deepest convictions only in manuscripts he kept locked away, writings that would not see daylight until centuries after his death. Newton's heresy centered on his conviction that God is absolutely one, not 3 persons sharing one substance. Christ was the Son of God and the Messiah, but not co-equal or co-eternal with the Father. The Holy Spirit likewise was not a distinct divine person, but rather the power or presence of God acting in the world. This made Newton an Arian, following the theology of Arius, an early Christian presbyter whose views the Council of Nicaea had condemned as heretical. According to Arian theology, only the Father is the supreme God, existing from eternity without beginning and possessing ultimate divine authority. The Son was begotten by the Father before all creation, and serves as the Father's agent in creating and governing the world, but the Son remains a created being rather than sharing fully in the Father's divine essence. This subordinationist theology preserved strict monotheism while acknowledging Christ's unique role in salvation history. Newton arrived at this position through both scriptural analysis and philosophical argument about the nature of divinity. He found no clear scriptural basis for Trinitarian formulas in the earliest biblical manuscripts. Later, textual additions appeared designed to support doctrines developed centuries after Christ, through church councils influenced by Greek metaphysics. The famous Johannine comma in 1 John chapter 5 verse 7 was a late interpolation completely absent from ancient Greek manuscripts. The verse reading there are three that bear record in heaven: the Father, the Word, and the Holy Ghost, and these three are one appeared to provide explicit scriptural warrant for the Trinity. But Newton's textual criticism revealed it as a marginal gloss that crept into the Latin Vulgate during the Middle Ages, never present in the original Greek text. This discovery convinced him that defenders of Trinitarian orthodoxy had corrupted Scripture itself to support their metaphysical innovations. Newton also argued that the Trinity involved logical contradictions and philosophical incoherence that no amount of appeal to divine mystery could resolve. How could three distinct persons share one substance while remaining genuinely distinct, rather than merely three aspects of one person? The Father sends the Son and both send the Spirit, implying temporal priority and hierarchical relation. Yet Orthodox theology insisted all three persons are equally eternal and necessary, existing in perfect equality without subordination. These claims seemed mutually incompatible to Newton's logical mind. If the Son is truly distinct from the Father, then they cannot be identically the same being. If they are identically the same being, then they cannot be truly distinct persons. Trinitarian theology attempted to have it both ways through elaborate metaphysical distinctions between substance and person, but Newton considered this verbal sleight of hand rather than coherent explanation. The doctrine introduced precisely the kind of occult qualities into theology that mechanical philosophy rightly eliminated from physics. Just as physics should avoid explaining phenomena through mysterious substantial forms, theology should avoid explaining God's nature through contradictory metaphysical formulations. Newton believed early Christians worshipped one God the Father and honoured Jesus as his appointed Messiah, without confusing the Son with the Father or claiming the Son possessed independent divine essence. The elaborate Trinitarian metaphysics emerged gradually through centuries of controversy, driven more by Greek philosophical influence than biblical revelation. Athanasius and his followers imposed this corruption through political manoeuvring at church councils and textual manipulation of scriptural manuscripts. Newton's massive manuscript attacking Athanasius detailed this alleged historical process with extensive documentation from patristic sources. He traced how theological terminology shifted during the 4th century, how political alliances shaped doctrinal outcomes at Nicaea, and how subsequent councils enforced Trinitarian orthodoxy while suppressing alternative views. This was not amateur conspiracy theory, but careful historical scholarship, arguing that institutional Christianity had betrayed original apostolic teaching. The corruption occurred not through malicious intent necessarily, but through the gradual influence of Greek philosophical categories ill-suited to Hebrew monotheistic revelation. Platonic ideas about eternal forms and divine emanations, Aristotelian metaphysics of substance and accident, Stoic concepts of logos and divine reason all infiltrated Christian theology during the patristic period. These philosophical imports transformed simple biblical faith into complex metaphysical system that ordinary believers could neither understand nor verify through Scripture. Newton saw his theological work as recovering original Christianity from centuries of accumulated corruption. parallel to his natural philosophical work recovering ancient wisdom about nature. This theological framework connected directly to Newton's natural philosophy in multiple fundamental ways. His absolute space and time replicated in physics his conception of God's absolute unity. Just as God is one and indivisible, so space and time are unified and cannot be decomposed into mere relations between bodies or events. The failure to distinguish absolute from relative quantities in physics reflected theological confusions about God's nature. Newton directly asserted that God's omnipresence literally constitutes space through his eternal existence everywhere. Duration and space are modes of God's existence rather than independent containers. This made space something quasi-divine rather than purely material reality. It explained why Newton insisted that everything, including minds and souls, must relate somehow to space. To exist means to exist somewhere, even for spiritual beings and God himself. Claiming God exists outside space was equivalent to atheism in Newton's view, a denial of God's reality disguised as reverence. His conception of divine action in the world also fundamentally shaped his physics. Newton believed God actively maintains the order of the universe through continuous providential intervention, rather than merely setting initial conditions and withdrawing. The stability of the solar system requires periodic divine adjustments to prevent accumulated perturbations from destroying orbital regularity. Comets passing through the system exert gravitational influences that gradually alter planetary motions. Without ongoing divine correction, these small perturbations would compound over time until the system collapsed into chaos. This contrasted sharply with the deist view that became popular among some Enlightenment thinkers. Deism imagined God creating the universe and then allowing it to operate as a perfect self-regulating mechanism requiring no further intervention. Newton considered this view both theologically objectionable and physically implausible. The evidence suggested continuous divine governance rather than autonomous, mechanical operation. Gravity itself might be direct divine action rather than mechanical push, transmitted through material medium. God's will continuously maintains the attractive forces between all material bodies throughout the cosmos. The mathematical law of inverse square describes how God chooses to govern planetary motion, but the force itself manifests ongoing divine activity in creation. This gave Newton's physics an actively theistic character, completely opposite to the deistic or materialistic interpretations later thinkers would impose. Newton also pursued what he called Principia theologia, the ancient theology revealed by God to Noah and the patriarchs before Moses. He believed this original religion consisted of pure monotheism and two simple moral commands given later by Christ. Love God with complete devotion and love your neighbour as yourself. This primordial revelation was known to all ancient peoples initially, but became corrupted over time through priestly manipulation and philosophical elaboration. Ancient Egyptians, Babylonians, and Greeks preserved distorted fragments of original truth in their mythologies and mystery religions. Pythagoras learned authentic wisdom during his travels in Egypt and transmitted it to disciples through symbolic teaching, encoding truths about nature and divinity in mathematical philosophy. According to Newton's reconstruction, ancient temples were built as models of the heliocentric cosmos, with sacred fires at their centres representing the sun as the central fire of nature. Temple worship and natural philosophy were united in original religious practice, with architectural forms encoding cosmological knowledge accessible to initiates who understood the symbolism. Newton wrote that one of the first institutions of true religion was proposing the frame of the world through temples as patterns helping people study the cosmos as the true temple of God. Ancient temples served as cosmological models, teaching initiates about planetary motions and the sun's central position. Religious architecture encrypted scientific truth available to those who could decode the symbolic language, This explained why ancient wisdom appeared in obscure allegorical forms rather than plain statement. Priests deliberately obscured profound truths to protect them from corruption by the uninitiated masses incapable of understanding properly. Newton himself adopted this ancient model of graduated disclosure, hiding deeper meanings in seemingly simple published statements. His framework of Prisca Theologia also shaped his approach to alchemy and natural philosophy more broadly. Alchemical texts might preserve ancient chemical knowledge transmitted through symbolic language, protecting it from distortion. Decoding these allegories could restore experimental methods and theoretical insights possessed by ancient practitioners. Newton was not discovering entirely new truths, but recovering what ancient sages already knew. This made his work restorative rather than revolutionary in his own eyes, aimed at recovering Prisca Sapientia, the ancient wisdom about natural and divine things that had declined from earlier heights. Isaac Newton purchased his first glass prism in 1666 while still an undergraduate student, beginning experiments that would revolutionize optics and ignite decades of bitter controversy. His discoveries challenged prevailing theories about light's nature and generated conflicts that shaped both his scientific method and his approach to intellectual combat. These disputes left psychological scars that influenced how Newton conducted research and published results for the rest of his life. The conventional wisdom held that white light is pure and simple, while colours represent modifications or corruptions of that purity. When light passes through glass, the material somehow alters pure white light to produce colours. The coloured spectrum visible through prisms arose because glass degrades or distorts light in various ways. This meant passing light through more glass should intensify the distortion, creating stronger or different colours. Newton's experiments demolished this theory with elegant simplicity that concealed profound implications. He passed white sunlight through one prism, which separated it into the familiar rainbow spectrum of colours. Then he passed the coloured spectrum through a second prism positioned to reverse the effect. The separated colours recombined perfectly into white light without any distortion or residue. This proved that colours are not corruptions of white light, but its components. White light is composite, a mixture of rays of different colours that ordinarily travel together but can be separated. The prism does not create colours by modifying light, but merely separates already existing components through differential refraction. Different colours correspond to light rays with different degrees of refrangibility through glass. Newton concluded that light itself exists in different varieties corresponding to different colours. Red light differs fundamentally from blue light in properties determining how each refracts when passing through transparent materials. Each colour has a characteristic angle of refraction when transitioning from air into glass. The spectrum displays this range of refraction angles for the rays composing white light. When all colours are present together in appropriate proportions, they produce the sensation of whiteness. When separated, each pure colour produces its own characteristic sensation. Colours are not qualities imposed on light by interaction with matter, but intrinsic properties of light itself. Newton presented these results in his first major publication to the Royal Society in 1672. The paper was titled "A Letter Containing His New Theory About Light and Colours." Newton asserted his experiments provided certain proof rather than hypothetical conjecture. He insisted the results followed geometrically and inevitably from experimental phenomena without requiring additional assumptions. Robert Hooke immediately attacked Newton's paper with numerous objections and alternative explanations. Hooke was England's leading optical authority and resented this upstart challenge from a young Cambridge scholar, relatively unknown outside university circles. He argued that Newton's theory depended on assuming light consists of particles or material bodies travelling through space. Since Hooke believed light propagates as waves or pulses through an ethereal medium, Newton's entire theoretical framework must be fundamentally mistaken. This criticism infuriated Newton because he considered it a complete misreading of his argument's logical structure. Newton insisted his theory of colour did not depend on any hypothesis about light's ultimate physical nature. Whether light consists of particles or waves or something else entirely, the experimental facts about different refrangibilities remain valid. Different types of light rays refract differently through glass, regardless of whether those rays are material corpuscles or wave motions. The theory represented demonstrated conclusions from experimental phenomena rather than speculative hypotheses about hidden mechanisms beyond observation. Hooke's insistence on conflating the theory with hypotheses about light's constitution showed exactly the kind of confused thinking Newton sought to eliminate from natural philosophy. Christian Huygens also criticised Newton's conclusions, though in more measured and philosophically sophisticated terms than Hooke's attacks. Huygens had developed an elaborate wave theory of light based on earlier ideas from Descartes and others. He showed that treating light as wave disturbances propagating through an elastic ether could explain reflection and refraction mathematically. His principle stated that every point on a wavefront acts as source, generating new spherical wavelets. The envelope of these wavelets forms the subsequent wavefront, allowing calculation of how waves propagate and change direction. Huygens found Newton's corpuscular assumptions unnecessary, and the experimental conclusions less decisive than Newton claimed. Alternative explanations could account for the phenomena without requiring that light itself exists in fundamentally different varieties. The debates about whether light consists of particles or waves would continue for over 2 centuries before quantum mechanics revealed both pictures capture partial truth about light's dual nature. Newton developed and defended corpuscular theory throughout his career, while Hooke and Huygens championed wave theories. Each approach could convincingly explain certain phenomena, while struggling with others that favoured the competing view. Corpuscular theory naturally accounted for rectilinear propagation and sharp shadows cast by obstacles. Newton argued that if light were waves, it should bend around barriers the way sound diffracts around obstacles. We hear sounds from around corners, but do not see light sources blocked by intervening objects. This suggested light travels in straight trajectories like particles, rather than spreading in all directions like waves through a medium. Later observations of diffraction through narrow slits would complicate this argument, but with available equipment the reasoning seemed compelling. Corpuscular theory explained reflection through elastic collision of particles bouncing off smooth surfaces at angles equal to their incident angles. Different sizes or speeds of corpuscles could account for different colours, having different refractive properties in transparent materials. Refraction occurred when corpuscles accelerated entering denser media, bending their trajectories toward the normal direction. This required light to travel faster in denser media, a prediction later proved false when measurements became possible. Newton acknowledged certain phenomena that seemed to require wave-like explanations, even within a fundamentally corpuscular framework. Thin films like soap bubbles display coloured interference patterns depending on film thickness, in ways corpuscular theory struggled to explain naturally. Light sometimes reflects and sometimes transmits through the same film without apparent difference in conditions determining the outcome. Newton proposed that corpuscles possess fits, alternately disposing them toward reflection or transmission as they travel. He suggested that corpuscles might create waves in the ether through their motion, with these waves overtaking corpuscles and causing periodic fits of easy reflection and easy transmission. This hybrid theory attempted to preserve corpuscular foundations while incorporating wave elements where phenomena demanded them. It demonstrated Newton's willingness to modify theory when phenomena required flexibility rather than rigid adherence to initial assumptions. The Optics, published in 1704 after Hooke's death, removed that psychological barrier, became Newton's comprehensive treatment of light and colour. Unlike the highly mathematical Principia written in Latin, the Optics appeared in English and remained accessible to educated readers without advanced mathematical training. The book detailed experiments readers could replicate themselves and carefully constructed arguments from observations. It included extensive queries proposing questions for further investigation rather than stating demonstrated conclusions. Newton used queries to engage in more speculative reasoning than the rigorous Principia style permitted. He asked whether light corpuscles might have different sizes corresponding to different colours, whether ethereal media with varying densities might explain optical phenomena, whether matter and light interact through forces analogous to gravity operating at small scales. These were explicitly not proven conclusions but suggestions for future natural philosophy to investigate. The queries showed how to pose productive questions directing research without making premature dogmatic claims. This methodology influenced subsequent science differently than the Principia despite the optic's less mathematical character. It provided a model for experimental investigation, combining careful observation with theoretical interpretation while maintaining appropriate epistemic humility. David Hume explicitly modelled his philosophical method on Newton's optical approach, attempting to do for human nature what Newton accomplished for light. The controversy with Hooke left lasting scars on Newton's personality and scientific practice. He became fearful of intellectual debate and delayed publishing major works for decades to avoid criticism. The Optics appeared in print only after Hooke's death in 1700. 3 removed the antagonist most likely to attack it. Newton's aversion to controversy meant that potentially valuable ideas remained secret throughout his life, shared only with small circles of trusted correspondents. The delayed publication cost science decades of progress that might have occurred if Newton's ideas had been available sooner for other investigators to build upon. Thomas Young's double-slit experiment in 1801 provided compelling evidence for wave theory that corpuscular assumptions could not easily accommodate. When light passes through 2 narrow slits, it creates interference patterns on a screen beyond. Bright and dark bands appear in regions where waves from both slits constructively or destructively interfere. This behaviour could not be explained by corpuscles travelling in straight lines through one slit or the other. If light consisted only of particles, we would expect 2 bright regions on the screen corresponding to the 2 slits with darkness between. Instead, the pattern showed multiple alternating bright and dark bands, the signature of wave interference. Throughout the 19th century, additional experiments on interference, diffraction and polarization confirmed wave theory's superiority over corpuscular approaches. Augustin Jean Fresnel developed comprehensive mathematical treatment of light as waves, explaining phenomena that had resisted Newtonian explanation. By century's end, wave theory dominated physics, and Newton's corpuscular approach seemed definitively refuted by accumulated experimental evidence. Then quantum mechanics in the early 20th century unexpectedly resurrected particle concepts in transformed form. The photoelectric effect, discovered around 1900, revealed that light ejects electrons from metal surfaces in ways wave theory could not adequately explain. The energy of ejected electrons depends on light's frequency rather than its intensity, contradicting classical wave predictions. Einstein proposed in 1905 that light consists of discrete energy packets, now called photons. Each photon carries energy proportional to frequency, and electrons absorb whole photons in quantum jumps rather than accumulating energy gradually from continuous waves. The photon model made light simultaneously particle and wave depending on experimental context. Modern physics recognizes wave-particle duality as fundamental to quantum mechanics rather than a paradox requiring resolution. Light displays wave behavior in interference and diffraction experiments. It displays particle behavior in photoelectric effect and Compton scattering experiments. Neither classical waves nor classical particles describe quantum entities adequately. They are quantum objects whose behavior incorporates aspects of both classical pictures without reducing to either. Newton's corpuscular theory thus anticipated certain aspects of modern photon theory, despite its incompleteness within classical physics. His intuition that light consists of discrete entities traversing space captured partial truth that wave theory alone missed. The dispute between Newton and Huygens could not be resolved within classical physics because both sides were correct and both were wrong in ways neither could imagine. They were describing complementary aspects of quantum reality, using inadequate classical concepts. The philosophical implications extend beyond optics to general questions about scientific progress and theory change. Newton and Huygens were not simply right or wrong, but captured different facets of phenomena that quantum mechanics would eventually unify in a framework foreign to both classical approaches. This suggests that scientific theories might be partially true in ways we cannot fully appreciate until more comprehensive frameworks emerge. The wars over light's nature shaped Newton's methodology as profoundly as his experimental discoveries. The attacks from Hooke convinced him that most natural philosophers lacked either the mathematical sophistication or the experimental care to evaluate rigorous work properly. He withdrew from public scientific debate, publishing only when absolutely necessary, and then with maximum caution about distinguishing demonstrated conclusions from speculative hypotheses. The Philosophiae Naturalis Principia Mathematica, published in 1687, stands as the most influential scientific work ever written. The author presented a mathematical system unifying terrestrial and celestial mechanics under common laws that applied equally to falling apples and orbiting planets. He demonstrated that the same force causing objects to fall on Earth governs the motion of the moon around Earth and planets around the Sun. This unification represented an intellectual achievement of staggering magnitude, transforming both the scope and methods of natural philosophy forever. The origins of the work lay in correspondence with Robert Hooke during 1679 and 1680. Hooke claimed to have discovered that planetary motion results from two component forces. Tangential motion continues by inertia, while a central force attracts the planet toward the Sun. The resulting orbit emerges from combining these two motions according to precise mathematical laws. Hooke suggested the central force decreases inversely proportional to the square of distance from the Sun. This inverse square law coincided with what Christopher Wren and Edmund Halley also suspected independently. But none of them could derive the empirical laws of planetary motion discovered by Johannes Kepler from this force law through mathematical demonstration. The mathematical derivation required techniques and insights they lacked, despite grasping the basic physical picture. The Cambridge professor had actually developed much of this mathematics years earlier, but had not published the results or shared them widely. In 1684, Halley visited Cambridge and asked whether an inverse square force produces elliptical orbits. The response came immediately, yes, and the calculation had already been completed years before. Unable to locate the previous work, the mathematician promised to rework the derivation and send it along. This question initiated the most intensive period of creative work in a career already marked by extraordinary productivity. The Principia emerged in less than 2 years of focused effort that contemporaries described as almost superhuman concentration. The project expanded far beyond the original question, becoming a comprehensive mathematical treatment of motion under various force laws and conditions. Book 1 developed general theorems about motion under central forces using geometric methods of remarkable sophistication and elegance. Book 2 analysed motion in resisting media and systematically demolished Cartesian vortex theories by showing they could not account for observed planetary motions. Book 3 applied the mathematical machinery to our actual solar system, deriving the motion of planets and moons from empirical observations using the theoretical framework established in earlier books. This represented a genuinely revolutionary achievement connecting abstract mathematics with observable celestial phenomena in unprecedented ways. The work showed how to derive the existence and mathematical form of universal gravitation from Kepler's empirical laws describing planetary orbits. Then it predicted corrections to Kepler's idealized laws based on mutual gravitational interactions between planets that Kepler had ignored or could not calculate. The Principia opened with definitions of fundamental concepts like mass, momentum, and force. These definitions gave precise mathematical meanings to terms previously used ambiguously in natural philosophy without clear operational content. Mass measured the quantity of matter in a body, determined by its density and volume together. Momentum equaled mass multiplied by velocity, representing the quantity of motion a body possesses at any moment. Force measured any action that changes a body's state of motion, whether accelerating it, decelerating it, or changing its direction. The famous scholium on absolute space and time followed these definitions, establishing metaphysical foundations before proceeding to physical laws. Then came the three laws of motion, forming the logical basis for all subsequent reasoning in the work. The first law stated that bodies preserve their state of rest or uniform motion unless forces act upon them. This principle of inertia was not an original invention, but borrowed from Descartes and Galileo, who had articulated similar ideas decades earlier. However, the Cambridge mathematician made it foundational and gave it precise formulation within a comprehensive dynamical framework. Inertia explained why planets continue moving without requiring continuous force to maintain motion, solving a puzzle that had troubled natural philosophers for centuries. Medieval thinkers had struggled with this question, often invoking impetus or other concepts to explain sustained motion after initial causes ceased operating. The first law eliminated the problem by making uniform motion, the natural state requiring no further explanation beyond initial conditions. Only changes in motion required causal explanation through forces acting on bodies. The second law stated that change of motion is proportional to impressed force, and occurs in the direction of that force. This provided the crucial quantitative relationship between force and resulting acceleration that makes mathematical physics possible as a predictive science. Modern textbooks express this as force equals mass times acceleration, though the original formulation used geometric language describing changes in momentum over infinitesimal time intervals. The second law allowed calculating how bodies respond to known forces, or inferring what forces must be acting from observed motions and accelerations. The third law stated that every action has an equal and opposite reaction acting on different bodies. When one body exerts force on another, the second body exerts an equal force back on the first in the opposite direction simultaneously. This was the most original contribution among the three laws, and proved essential for analysing complex systems involving multiple interacting bodies. It guaranteed that internal forces within a system cancel out when calculating total momentum, which must remain conserved. When a horse pulls a cart, the cart pulls back on the horse with equal force in the opposite direction. When Earth attracts the Moon gravitationally, the Moon attracts Earth with equal gravitational force, causing both bodies to orbit their common centre of mass. These mutual interactions obey perfect symmetry regardless of the body's sizes, masses, or other properties. From these principles emerged numerous theorems using geometric methods of great ingenuity and complexity that few contemporaries could follow. The work proved that a central inverse square force produces elliptical orbits, with the force centre located at one focus of the ellipse. It showed how orbital period relates to distance following Kepler's third law, exactly when gravitational interactions are considered. These results confirmed Kepler's empirical laws by deriving them from fundamental dynamical principles rather than accepting them as brute observational facts. Book 3, titled The System of the World, applied abstract mathematics to real astronomical observations compiled over centuries. The book began with 6 phenomena describing observed regularities in planetary and lunar motions drawn from the best available data. Then the rules of reasoning were applied to derive the law of universal gravitation from these observational patterns through systematic mathematical argument. This reasoning combined rigorous mathematics with careful attention to empirical constraints observational uncertainties, and measurement errors. The work showed that the Moon's centripetal acceleration toward Earth equals the acceleration of falling objects at Earth's surface when properly adjusted for the difference in distance. The calculation required determining the force needed to maintain the Moon's observed orbit and comparing it to terrestrial gravity diminished by the square of the ratio of distances. The match confirmed that the same force operates on Earth and in the heavens, eliminating the ancient Aristotelian distinction between terrestrial and celestial realms with different physics. All matter throughout the cosmos obeys identical physical laws without exception. Then the analysis demonstrated that all planets and their satellites follow the same inverse square law in their respective systems with mathematical precision. Jupiter's moons orbit Jupiter, Saturn's moons orbit Saturn, and all these systems exhibit the same mathematical relationships between period and distance. The satellites of Jupiter follow the same laws governing Earth's moon, proving that gravity operates universally rather than being peculiar to Earth alone. Each planet with satellites demonstrates the inverse square relationship independently, providing multiple confirmations through different observational systems. Every gravitational system throughout the solar system operates according to the same mathematical principles. The force varies directly with the product of the masses involved and inversely with the square of distance separating them. This universal law applied to every material body everywhere, from tiny pebbles to massive planets and the Sun itself. The mathematical formula stated that force equals the product of the two masses divided by the square of distance between their centres. This gave a precise quantitative law replacing qualitative explanations of celestial motion that had prevailed since antiquity. Every particle of matter attracts every other particle according to this mathematical relationship without exception or variation. The implications were staggering, suggesting fundamental unity underlying all physical phenomena throughout the entire cosmos. The method involved idealizing complex situations, then systematically adding complications to increase correspondence with observations. First came solutions for two-body problems where only two masses interact gravitationally with each other in isolation. Then perturbations from third bodies were added, along with corrections for non-spherical mass distributions and other complicating factors. Each step increased agreement between theoretical predictions and actual measurements recorded by astronomers. Calculations accounted for corrections to lunar motion caused by the Sun's perturbing influence on the Earth-Moon system. The work explained the precession of Earth's axis through tidal forces acting on the planet's equatorial bulge from Sun and Moon. It showed how mutual gravitational attraction between Jupiter and Saturn slightly distorts their orbits in observable ways. These detailed corrections demonstrated how to extract precise predictions from complex real-world phenomena involving multiple interacting bodies. The Principia also derived the theory of tides from gravitational principles with remarkable success. Ocean tides arise from differential gravitational forces exerted by Moon and Sun on Earth's oceans at different locations. The mathematics calculated how tide height depends on the positions of Moon and Sun throughout their cycles and orbital configurations. Predictions matched observed tidal patterns in detail, providing spectacular confirmation of the gravitational framework through an entirely different class of phenomena. Yet fundamental limitations and unresolved problems remained despite the theory's extraordinary explanatory and predictive success. The work established that gravity exists and acts according to precise mathematical laws derivable from observations, but it could not explain how gravity operates or what mechanism transmits force across empty space without material contact. Action at a distance without physical contact seemed philosophically problematic, or even occult to many natural philosophers. Critics, especially on the continent, attacked this aspect as a retreat from mechanical philosophy's standards of explanation. Descartes and Leibniz had insisted that matter affects matter only through direct physical contact between bodies. Gravitational attraction across vacuum violated this mechanical principle, apparently reintroducing Aristotelian occult qualities that mechanical philosophy aimed to eliminate from natural explanation. Continental followers struggle to defend the theory against these philosophical objections despite its mathematical success. The response emphasized that mathematical description of gravity's actions sufficed for natural philosophy even without knowing the underlying cause. The theory had demonstrated that gravity genuinely exists and acts according to discovered laws with extraordinary precision. These laws explain and predict enormous ranges of phenomena, from falling apples to planetary orbits to oceanic tides. Whether gravity operates through unknown mechanisms or acts directly across space remained an open question for future investigation. Publishing speculations about mechanisms without experimental foundation would violate the methodological principles against feigning hypotheses. The private manuscripts reveal speculation about ethers or subtle fluids that might mechanically transmit gravitational effects through space. But these remained unpublished speculations, never presented as demonstrated truths derived from phenomena. Better to acknowledge ignorance about mechanism than to invent unverified explanations merely to satisfy philosophical preferences for contact action. This methodological stance represented profound shift in what counted as legitimate scientific explanation and adequate understanding. Previous natural philosophy demanded identifying causes and mechanisms underlying all observed effects as essential for genuine knowledge. The new approach argued that mathematical description of how phenomena behave could constitute adequate knowledge for practical and theoretical purposes. We need not know why gravity follows an inverse square law to use that law successfully for prediction, explanation, and technological application. The distinction between knowing that and knowing why became central to subsequent philosophy of science and debates about scientific realism. Demanding mechanical explanations might be premature before sufficient phenomena are examined thoroughly and mathematical relationships established firmly. Better to secure mathematical descriptions than to multiply unsupported hypothetical mechanisms that may prove entirely wrong. Yet the search for deeper explanations never ceased despite this methodological caution about premature theorizing. The queries appended to later editions of the Optics proposed questions about whether gravity might result from density gradients in ethereal fluids. Perhaps space contains subtle matter with varying density that pushes bodies toward regions of lower density through pressure differences. Such mechanical explanations remained possible, and worth investigating once the mathematical framework was established securely. The work's theological dimension proved inseparable from its physical content despite later attempts at separation. The General Scholium, added to the second edition in 1713, contained explicit theological arguments and claims. God exists always and everywhere, sustaining the order of creation through continuous providential action rather than merely setting initial conditions. The stability of the solar system requires ongoing divine management to prevent accumulated perturbations from destroying orbital regularity over long periods. Comets passing through the system exert gravitational influences that gradually alter planetary motions in ways that would compound destructively without correction. This theological framework made the physics actively theistic rather than deistic or materialistic in its ultimate foundations and implications. Gravity itself might manifest direct divine action rather than mechanical push transmitted through material medium, filling space. God's will continuously maintains attractive forces between all material bodies throughout the cosmos according to the mathematical law discovered. The inverse square relationship describes how God chooses to govern planetary motion and terrestrial gravity through lawful, regular action. The law of nature is divine will, manifesting through regular, predictable operations rather than arbitrary, miraculous interventions. This gave the entire system a theological character that Enlightenment interpreters would later strip away while appropriating the mathematics. The unified theory of terrestrial and celestial mechanics represented the fulfillment of ancient dreams about mathematical natural philosophy. Pythagoras and Plato had believed nature operates according to mathematical harmonies, but lacked the tools to demonstrate this rigorously. The Principia finally realized that ancient vision, through sophisticated mathematics applied to careful observations accumulated over centuries. The work showed that mathematical relationships govern the physical world with precision, making nature comprehensible to human reason despite its vast complexity. Over 1 million words filled manuscripts devoted to alchemy and chemical processes, representing decades of intensive systematic investigation. These were not casual notes or idle curiosities, but serious research pursued with the same rigour applied to mathematical physics. The Cambridge professor painstakingly transcribed alchemical text by hand, conducted dangerous experiments in a private laboratory, and developed theories about active principles operating in matter at microscopic scales. For the natural philosopher, alchemy constituted legitimate investigation equal in importance to optics or celestial mechanics. The modern separation between chemistry and alchemy did not exist during the 17th century as it would emerge later. Both disciplines investigated properties and transformations of matter through observation and controlled experimentation. Alchemy included metallurgy, medicine, dye production, and other practical chemical arts alongside more speculative pursuits. The goal of transmuting base metals into gold represented the extreme end of a spectrum that encompassed legitimate empirical investigation throughout. Alchemical research aimed at understanding forces operating at the smallest scales of material existence beyond what crude mechanical philosophy could explain adequately. The mechanical philosophers like Descartes attempted to explain all phenomena through size, shape, and motion of matter particles alone. According to this view, particles collide and interact mechanically, like machine parts, fitting together through geometric complementarity. Chemical reactions occurred when particles with appropriate shapes interlocked or separated based purely on mechanical considerations. But this framework could not explain chemical affinity, where certain substances preferentially combine while rejecting others despite similar mechanical properties. Why does acid dissolve some metals but leave others untouched, even when their densities and mechanical characteristics appear similar? Why do particular salts crystallize in specific geometric forms rather than random arrangements? These selectivity suggested forces guiding combinations beyond what mechanical collision alone could produce. The investigator suspected that chemical phenomena revealed active principles beyond purely mechanical interactions operating at scales too small for direct observation. Particles might attract or repel each other through forces analogous to gravity, but operating at different distance scales. These microscopic forces could explain selective chemical combinations, crystal formation, solution and precipitation, and numerous other phenomena resisting mechanical explanation. Alchemy provided experimental evidence for matter's behaviour that mechanistic philosophy could not accommodate within its restricted framework. Understanding these active principles might unlock deeper truths about matter's fundamental nature and the hierarchies of power operating throughout creation. The philosopher's stone represented matter in its most active and perfected state, embodying maximum virtue or transformative capacity. Transmutation might become possible by transferring these active principles to base metals, fundamentally altering their essential natures through natural processes. This was not supernatural magic, but natural philosophy, extended into domains where mechanical explanations proved insufficient. Chemical investigation complemented mathematical physics by exploring aspects of divine action in matter that equations could not capture fully. Both aimed at revealing how God works in creation, using different methods appropriate to different scales and types of phenomena. The manuscript titled Of Nature's Obvious Laws and Processes in Vegetation analysed plant growth using alchemical concepts and frameworks. It proposed that active principles attract appropriate particles from soil and air into growing structures through selective affinities. This selective attraction explained why plants absorb certain elements while excluding others despite all being mechanically available. The process resembled chemical reactions where specific substances combine according to intrinsic affinity rather than random mechanical encounter. The Cambridge laboratory, adjacent to Trinity College chambers, contained furnaces, distillation equipment, and supplies of mercury, antimony, lead, and other materials. Experiments conducted there involved heating substances, observing colour changes, measuring weights, and recording transformations under varying conditions. The systematic approach matched the rigour applied to optical experiments with prisms, varying conditions methodically and maintaining detailed records. Dangerous mercury vapours and toxic antimony compounds posed serious health risks that the experimenter accepted as necessary for advancing knowledge. Mercury poisoning symptoms appeared periodically, including tremors, mood changes, and cognitive difficulties that contemporaries noted with concern. Yet the research continued despite these dangers, because the questions seemed too important to abandon over mere physical discomfort. The alchemical texts Newton transcribed used symbolic and allegorical language that required interpretation to extract practical meaning. Dragons devouring themselves, green lions, philosophical mercury, and other images encoded chemical processes and substances through metaphor. This deliberate obscurity protected secrets from uninitiated readers incapable of understanding properly or likely to misuse knowledge. The investigator approached these texts as containing genuine wisdom transmitted through symbolic protection, similar to how ancient temples encoded cosmological truths in architectural forms. Decoding the allegories might restore experimental methods and theoretical insights possessed by ancient practitioners who understood matter's active principles. This connected directly to the broader Prisca Sapientia project of recovering ancient wisdom corrupted or lost over centuries. Alchemical knowledge represented another stream of ancient understanding that required patient study and experimental verification to restore. The philosopher did not accept alchemical authorities uncritically, but tested claims through laboratory work, attempting to replicate described processes and observe predicted transformations. When texts promised specific results, experiments checked whether those results actually occurred under stated conditions. This empirical approach unified the method across domains where others saw fundamentally different kinds of investigation, requiring separate standards. Knowledge always required empirical grounding regardless of subject matter, whether studying light refraction, planetary orbits, biblical chronology, or chemical transformations. The mathematical dimension also connected alchemical investigation to other research, though less obviously than in physics. Careful measurement of weights before and after reactions provided quantitative data about material transformations and conservation principles. Ratios and proportions in combining substances suggested mathematical relationships governing chemical processes similar to laws governing motion. Temperature measurements, timing of reactions, and geometric crystal forms all involved mathematical description and analysis. The conviction that mathematics reveals divine rationality ordering creation extended to chemistry as much as celestial mechanics. God's rational mind structured matter at all scales according to principles human investigation could discover through careful study. Ancient philosophers like Pythagoras understood this mathematical character of reality, which explained their emphasis on number and proportion in natural philosophy. The extensive alchemical work posed acute problems for executors after death in 1727. Publishing these manuscripts would suggest England's greatest scientific mind wasted decades on irrational pursuits when he could have advanced legitimate science further. The Enlightenment increasingly viewed alchemy as fraudulent or mystical rather than empirical, making the association potentially damaging to reputation. Yet the sheer volume of material and obvious seriousness with which it had been pursued made simple dismissal difficult. The executors chose concealment, keeping alchemical manuscripts private and unavailable to scholars for over 2 centuries. Only in the 20th century did these texts begin emerging through auction sales and private collections, becoming accessible to researchers. Their revelation revolutionized understanding by showing that theology and alchemy consumed more time and energy than the physics for which the author became famous. The interest in active principles fundamentally linked alchemical investigation to published physics despite their apparent separation. Gravity itself might be an active principle rather than purely mechanical force transmitted through contact. Matter might possess intrinsic tendencies towards specific motions beyond simple inertia, described in the first law of motion. These ideas contradicted mechanical philosophy's program of explaining everything through passive matter and contact forces alone. The queries added to later editions of the Optics most clearly expressed these speculations about forces between particles. Do particles of matter possess forces allowing them to attract at small distances? The queries asked. These short-range forces operating at microscopic scales might explain chemical reactions, surface tension, capillary action, and other phenomena. A hierarchy of forces at different scales could unify chemistry and physics under common principles while explaining their apparent differences. Universal gravitation operated over astronomical distances between massive bodies following inverse square law. Chemical forces operated over molecular distances between tiny particles following different mathematical relationships. Electric and magnetic forces operated over intermediate scales with their own characteristic behaviours and mathematical laws. Heat might involve forces between particles at the smaller scales, affecting their motions and configurations. This vision anticipated later physics that would indeed unify forces under mathematical theories, though not in the forms the alchemist imagined. The suggestion that nature operates through mutual attraction and repulsion of smallest particles at various distance scales proved profoundly insightful. These forces vary with distance according to mathematical laws, possibly analogous to gravity's inverse square relationship. Chemical affinity, heat, electricity and magnetism might all relate to particle-level forces operating according to discoverable principles. The speculative framework proved more prescient than the specific mechanisms proposed, pointing toward productive research directions even when particular details failed. Some scholars argue that alchemical work directly influenced the conception of gravity as non-mechanical force operating through empty space. The doctrine that matter possesses active principles derived from chemistry might have suggested forces in physics beyond mechanical collision. The philosopher's stone represented matter in maximally active form, analogous to how gravity represents a universal active principle pervading all matter everywhere. Both alchemy and gravitational theory violated strict mechanical philosophy by attributing to matter powers beyond passive extension and motion. Other scholars emphasized discontinuities between private alchemy and public physics, noting the rigorously mathematical style of the Principia contains no hint of alchemical concerns or terminology. The published natural philosophy deliberately excluded alchemical reasoning from its demonstrations, even if such ideas influence background thinking. The separation between secure mathematical proofs and speculative chemical theories remained strict in what reached publication. Both perspectives capture partial truth about complex intellectual practice that freely moved between different domains while maintaining distinctions. The mind synthesized insights from mathematical mechanics, optical experiments, chemical operations, and theological investigations into coherent worldview. Connections and analogies appeared everywhere that subsequent generations trained in separate disciplines would miss entirely. The unity existed in underlying vision even when not explicit in published texts designed for different purposes and audiences. Modern chemistry confirmed some alchemical intuitions while completely rejecting others as the science developed through the 18th and 19th centuries. transmutation became possible through nuclear reactions discovered in the 20th century, though not via philosopher's stone or chemical processes. Chemical reactions genuinely involve forces between atoms, as the alchemists suspected, though not purely mechanical collisions. Elements transform into others through radioactive decay and nuclear fusion, vindicating the ancient dream of transmutation in unexpected form. The active principles governing matter proved to be electromagnetic forces between charged particles and nuclear forces binding atomic nuclei. These forces operate according to mathematical laws as hoped, though the quantum mechanical framework differs radically from classical mechanics. The experimental technique influenced subsequent chemistry despite theoretical framework's ultimate failure. Careful systematic experimentation with detailed record-keeping became standard practice in chemical investigation during the 18th century. The search for quantitative laws of chemical reactions followed the mathematical approach pioneered in physics, seeking numerical relationships. Later chemists separated valid experimental methodology from invalid alchemical theories, preserving empirical rigor while abandoning philosophical frameworks. The alchemical quest thus contributed to scientific development indirectly through methodological influence, even as its specific goals remained unachieved. The active principles sought in chemical transformations proved to be electromagnetic and quantum mechanical effects beyond 17th century conceptual resources. The vision of understanding matter through forces operating at multiple scales pointed toward productive research even when particular implementations failed. The dedication to empirical investigation and quantitative measurement established standards that transcended the theoretical mistakes. This pattern appears repeatedly in the history of science, where research programs produce valuable results even when their guiding theories prove incorrect. Pursuing wrong ideas rigorously sometimes advances knowledge more than avoiding error through excessive caution and timidity. The alchemical manuscripts reveal someone wrestling with genuine puzzles about material transformations that mechanical philosophy could not explain adequately. Why do substances combine selectively rather than randomly? What determines crystal structures and chemical properties of different elements? How do living things extract specific materials from soil to build organized structures? These questions required answers beyond what mechanism alone could provide, even if the alchemical framework proved inadequate ultimately. Modern molecular chemistry and quantum mechanics eventually answered these questions, but the problems themselves were legitimate and the mechanical philosophy's limitations real. The investigation rightly identified inadequacies in prevailing explanatory frameworks, even if the alternative framework proposed failed equally. Block 8. Principia Theologia and Ancient Wisdom. The conviction that ancient civilizations possessed profound knowledge about nature and divinity, later corrupted or lost, shaped every aspect of intellectual work across decades. This was not romantic nostalgia for a golden age, but a systematic interpretive framework that unified natural philosophy, theology, and historical investigation into a coherent research program. The belief held that God had revealed fundamental truths to Noah and the patriarchs before Moses, forming an original pure religion that all peoples initially shared. Recovering this Principia Theologia, this ancient theology, became a driving mission that gave ultimate meaning to pursuits in physics, chronology, and biblical scholarship. The original revelation consisted of simple truths accessible to reason and confirmed by Scripture. One God created and governs all things, demanding worship and moral obedience from his creatures. 2 commandments summarized all ethical duty: love God completely and love your neighbor as yourself. This uncomplicated monotheism with clear moral demands constituted the religion revealed to the earliest humans and transmitted through Noah's descendants after the flood. Ancient sages in Egypt, Babylon, Persia, and Greece preserved fragments of this wisdom, while their priests corrupted it into elaborate polytheistic systems. Pythagoras learned authentic knowledge during travels to Egypt and the East, then transmitted it to disciples through symbolic teaching designed to protect truths from the uninitiated. His mathematical philosophy and heliocentric cosmology represented genuine understanding of natural and divine realities rather than mere speculation or lucky guesses. Similarly, original Christianity worshipped the one God and honoured Jesus as the promised Messiah without confusing the Son with the Father or inventing Trinitarian metaphysics. The elaborate doctrines emerged through Greek philosophical influence corrupting Hebrew monotheism over centuries following Christ's apostles. Recovering pristine ancient wisdom required critical study of texts, careful historical reconstruction, and willingness to question authorities who had distorted original teachings. The massive manuscript titled The Original of Religions reconstructed how corruption occurred through detailed analysis of ancient sources. The work traced how Egyptian priests transformed monotheism into complex pantheons while retaining esoteric knowledge in mystery religions. It showed how Phoenician traders spread religious ideas throughout the Mediterranean, creating syncretism between originally pure traditions. It documented how Greek philosophers borrowed from earlier Egyptian and Babylonian wisdom, while adding their own elaborations and distortions. This historical scholarship aimed to separate authentic ancient knowledge from later corrupting additions, parallel to textual criticism that identified interpolations in biblical manuscripts. Ancient temple architecture encoded cosmological knowledge accessible to those who understood the symbolic language employed by initiated priests. The Temple of Solomon and pagan temples dedicated to Vesta used circular designs with sacred fires at their centres representing the sun. These architectural features symbolized heliocentric cosmology, where the sun occupies the central position in the planetary system. Temple worship and natural philosophy united in original religious practice before later corruption separated them into distinct domains. The investigator wrote that proposing the frame of the world through temples constituted one purpose of the first true religious institutions. Temples served as cosmological models, teaching initiated members about planetary motions and the sun's centrality through architectural symbolism. Religious ritual encoded scientific truth available to those trained to decode the representations properly. This explained why ancient wisdom appeared in obscure allegorical forms rather than plain direct statement of facts. Priests deliberately obscured profound truths to protect sacred knowledge from corruption by uninitiated masses incapable of proper understanding. Only those who underwent proper training and demonstrated worthiness received full explanation of the symbolic meanings. This hierarchical knowledge system prevented distortion while maintaining authentic traditions across generations despite external threats. The natural philosopher adopted this ancient model in handling profound discoveries and controversial conclusions, concealing deeper theological meanings in seemingly straightforward published statements, protected dangerous ideas from premature exposure while making them available to discerning readers. The general scholium was written to be understood at multiple levels depending on the reader's preparation and insight. Ordinary readers found mathematical physics and empirical demonstrations of gravitational theory sufficient for practical purposes. Adept readers recognized theological subtext about God's omnipresence, constituting space and continuous divine action, maintaining cosmic order. The deepest level remained accessible only to those who grasped the anti-Trinitarian implications and connections to ancient wisdom. This created deliberate ambiguity, allowing communication with different audiences simultaneously through carefully constructed text, admitting multiple interpretations. The framework of ancient theology also shaped the approach to alchemical texts as potentially preserving chemical knowledge transmitted symbolically. Dragons, lions, philosophical mercury, and other allegorical images might encode genuine experimental procedures and theoretical insights when properly decoded. These were not meaningless fantasies, but symbolic protection, for knowledge that uninitiated readers would misunderstand or misuse harmfully. Patient study combined with experimental verification could restore what ancient practitioners understood about active principles in matter. The work of recovering ancient wisdom thus proceeded simultaneously across multiple domains using adapted methods appropriate to each. Natural philosophy required mathematical analysis of phenomena and careful experimentation to rediscover physical laws ancient sages had known. Biblical scholarship required textual criticism to remove corrupting additions and restore original meanings obscured by later editors. Chronological investigation required astronomical calculation to establish accurate dating for ancient events, correcting inflated timelines that exaggerated civilization's antiquity. All these investigations contributed to the unified project of recovering Prisca Sapientia, the ancient wisdom that had declined over centuries. The chronology of ancient kingdoms amended represented decades of work, establishing accurate timelines for ancient history using astronomical methods. Ancient texts contained references to celestial events like eclipses, planetary configurations, and stellar positions observable at specific times. Calculating backwards to determine when described astronomical phenomena actually occurred allowed precise dating of historical events mentioned in connection. This mathematical chronology could correct errors in traditional dating schemes that relied on unreliable king lists and contradictory records. The work argued that standard chronologies exaggerated the antiquity of Egyptian and Greek civilizations by several centuries, making them appear older than biblical patriarchs. By correcting these errors through astronomical calculation, the investigator showed that all ancient wisdom derived ultimately from Hebrew revelation rather than independent pagan sources. This vindicated the priority and authenticity of biblical revelation over supposedly older traditions that might claim precedence. Egyptian priests had not possessed knowledge predating Noah, but rather received it through the dispersion of peoples after Babel. Greek philosophers had not independently discovered truths about the cosmos, but learned them from travels to Egypt, which preserved Noahic traditions imperfectly. Demonstrating the correct chronology destroyed claims that pagan wisdom antedated or exceeded Hebrew revelation in antiquity or profundity. The project involved detailed analysis of mythological traditions across different cultures, seeking common origins beneath surface variations. The same basic stories appeared in Greek, Egyptian, and Near Eastern mythology, with modifications reflecting local circumstances and cultural transmission. These parallels suggested one original source that different peoples preserved and modified according to their specific histories and corrupting influences. Comparative mythology revealed historical connections between ancient peoples and traced how knowledge was transmitted through trade, conquest, and cultural exchange. Phoenician sailors spread ancient wisdom through maritime trade routes connecting Mediterranean civilizations separated by water but linked economically. They transmitted astronomical knowledge, religious concepts, and philosophical ideas across the ancient world through commercial networks. This explained similarities between distant cultures that had no obvious direct contact through land routes or military conquest. Ancient globalization had occurred through seaborne commerce, creating cultural exchanges invisible to historians, focused only on political and military history. The study of how ancient mystery religions preserved esoteric knowledge through initiatory practices revealed sophisticated systems for protecting truth. The Eleusinian mysteries and similar cults guarded secrets from public disclosure through graduated revelation across initiatory stages. Participants learned progressively deeper truths as they advanced through ritual grades, proving their worthiness and capacity for understanding. This hierarchical knowledge system prevented corruption of profound ideas while maintaining authentic traditions despite external pressures and dangers. The parallel between ancient mystery religions and the investigator's own practice of concealment became explicit in private reflections. Just as ancient initiates protected monotheistic truth from polytheistic corruption through secrecy, modern investigation protected anti-Trinitarian Christianity from orthodox persecution through strategic concealment. Just as temple architecture encoded cosmological knowledge for initiates, published works encoded theological meanings for readers prepared to understand. The Pythagorean style of hiding deep significance in seemingly simple statements became a deliberate rhetorical strategy. The Principia Theologia framework also directly shaped interpretation of natural philosophical discoveries as recovering rather than inventing knowledge. Ancient sages had understood that Earth moves around the sun, that mathematical laws govern celestial motions, and that space extends infinitely. Medieval corruption had replaced this genuine knowledge with Ptolemaic epicycles and Aristotelian crystalline spheres carrying planets. The Copernican revolution and subsequent mathematical physics represented restoration rather than innovation, returning to truths known millennia earlier. This interpretive framework made revolutionary scientific work appear conservative in its own self-understanding, aimed at restoration rather than rejection of tradition. Modern philosophy had declined from ancient heights, achieved by Pythagoras and Egyptian priests who understood mathematical structure underlying phenomena. The goal was recovering lost knowledge rather than creating entirely new systems, unprecedented in human history. This conservative self-presentation concealed genuinely radical innovations by portraying them as ancient wisdom finally restored after long corruption. The tension between actual innovation and claimed restoration created productive ambiguity in how work could be received by different audiences. Orthodox readers could view gravitational physics as recovering ancient mathematical philosophy, compatible with Christian theology properly understood. Heterodox readers could recognize anti-Trinitarian implications and connections to pre-Christian monotheistic wisdom that Christianity had corrupted in the 4th century. Both readings found textual support because both dimensions genuinely existed in the author's synthetic vision, uniting multiple intellectual streams. The biblical chronology attempted to establish accurate dating for prophesied events, using the day-year principle applied to Daniel and Revelation. Each prophetic day corresponded to an actual year in historical time, allowing calculation of when predicted events would occur. The corruption of Christianity began when Charlemagne was crowned Holy Roman Emperor in 800, establishing the political religious system dominating Europe. The restoration of true religion would not occur until approximately 2060, giving a time frame of 1260 years for the prophesied apostasy. This calculation suggested the investigator lived during the long period of corruption prophesied in Scripture, unable to see the restoration, but able to prepare for it through recovering authentic wisdom. Natural philosophical work and theological research both contributed to this preparation by establishing truths that future generations would need. The emotional and spiritual stakes in recovering ancient wisdom exceeded even the intellectual challenges involved in the research itself. This was not merely academic curiosity about historical questions, but a sacred mission to prepare for God's eventual restoration of true religion and knowledge. Every discovery in physics revealed God's ways of acting in creation, contributing to proper understanding of divine nature and purposes. Every correction to chronology clarified Scripture's prophetic timeline, showing how history unfolds according to divine plan. Every theological manuscript arguing against Trinitarian corruption defended original apostolic Christianity against centuries of accumulated error. These were not separate projects, but aspects of one comprehensive effort to recover what God had revealed to ancient sages and prophets. The unity of vision made possible the extraordinary productivity across such diverse fields requiring different technical skills. Someone, viewing these as unrelated hobbies, misunderstood completely the underlying coherence and driving purpose unifying everything. Modern scholars debate how seriously to regard the Principia Theologia framework when interpreting the natural philosophical work. Some treat it as peripheral interest, separate from serious scientific investigation into physics and mathematics. Others argue it fundamentally shaped motivation and interpretive strategies throughout all research, making it essential for understanding the work holistically. The evidence suggests the framework genuinely occupied a central rather than peripheral position in the author's self-understanding and intellectual identity. The massive chronological manuscripts received as much careful attention and revision as the Principia across decades of sustained effort. The theological writings arguing for original monotheism exceeded all mathematical and physical works combined in sheer volume of text produced. This cannot be dismissed as casual hobby pursued in spare moments between real investigations of nature. The ideas transformed philosophy as profoundly as they revolutionized physics and mathematics. Every major thinker of the 18th century Enlightenment grappled with implications of this work, whether embracing or resisting its conclusions. The methodology, metaphysics, and mathematical achievements defined philosophical agendas for 2 centuries after publication. Understanding this period requires recognizing the central role these ideas played philosophically, not merely scientifically. John Locke knew the Cambridge professor personally, and their philosophical views influenced each other through years of correspondence and conversation. Locke's empiricism emphasized sensory experience as the foundation of knowledge, rejecting Cartesian innate ideas as unnecessary philosophical baggage. This aligned with experimental philosophy and skepticism toward purely rationalist metaphysics that claimed knowledge through reason alone. Both insisted that careful observation must constrain theoretical speculation rather than allowing unbounded system building detached from phenomena. However, Locke also recognized limits to what sensory experience alone could establish about nature's ultimate structure. He distinguished primary qualities like extension and motion from secondary qualities like color and taste, in ways reflecting the new mechanical philosophy. Primary qualities belonged to objects themselves, while secondary qualities depended on perceiving minds and sensory apparatus. This distinction attempted to reconcile mathematical natural philosophy with empirical epistemology that grounded knowledge in experience. The Cambridge work influenced Locke's thinking about space, substance, and our knowledge of material reality in ways evident throughout the essay concerning human understanding. Locke struggled with whether space is substance, property, or pure relation, never reaching completely satisfactory resolution. The concept of absolute space offered one possible answer, though Locke never fully endorsed it without reservations. Their correspondence reveals ongoing dialogue about fundamental metaphysical and epistemological questions that neither resolved definitively. George Berkeley developed idealist philosophy, partly in response to the new mechanics and Lockean empiricism combined. Berkeley rejected material substance entirely, arguing that only minds and ideas genuinely exist. Physical objects are collections of sensory ideas perceived by minds rather than material substances existing independently. This radical move eliminated the gap between appearance and reality that troubled Locke's representational theory of perception. If objects just are collections of perceptions, then we directly apprehend reality rather than inferring it from sensory intermediaries. Berkeley also criticized absolute space and the new calculus on both philosophical and mathematical grounds. He argued that absolute space existing independently of perception made no empirical sense as a concept. How could we have any idea of space if not derived from spatial relationships between perceived objects? Absolute space transcending all possible experience remained an empty notion without empirical content or meaning. The calculus relied on incoherent notions of infinitesimal quantities that were neither something nor nothing definite. These fluxions or infinitely small magnitudes violated clear logical principles, yet produced correct mathematical results mysteriously. Berkeley's critique in The Analyst exposed genuine foundational difficulties that would require centuries to resolve through rigorous analysis. These objections revealed real vulnerabilities in metaphysical and mathematical foundations despite the practical success of theories built upon them. David Hume undertook the most systematic attempt to apply the experimental method to human nature and morality directly. His treatise of human nature bore the subtitle, An Attempt to Introduce the Experimental Method of Reasoning into Moral Subjects, explicitly modelling itself on the optical and mechanical work. Hume aimed to do for psychology and ethics what the Principia accomplished for physics by discovering empirical regularities and deriving general principles explaining them. This required identifying patterns in mental life comparable to physical laws governing material motion. Hume's analysis of causation directly engaged the methodology and its philosophical foundations with devastating implications. The Cambridge philosopher claimed to derive gravity's existence from phenomena using induction without feigning hypotheses, but Hume argued that induction itself lacks rational foundation beyond custom and psychological habit formed through repeated experience. We cannot demonstrate that unobserved cases will resemble observed ones, since any argument for induction's reliability would itself rely on inductive reasoning. This creates vicious circularity, making induction rationally unjustifiable despite its practical indispensability. Causation reduces to constant conjunction of events in our experience, rather than necessary connection perceived directly. We observe that certain event types regularly follow others, and form expectations accordingly through psychological conditioning. But we never perceive necessary connections between causes and effects themselves, only regular temporal sequences. The idea of causal power or necessity is psychological projection, rather than empirical discovery about external reality. This skeptical argument threatened to undermine the entire Newtonian framework philosophically, even while accepting its practical utility. If induction lacks rational justification, then conclusions drawn from phenomena remain unjustified beliefs despite their predictive success. The laws of motion and gravitation possess no greater epistemic warrant than customary expectations formed through habit. Mathematical demonstrations cannot overcome the fundamental problem that inductive generalization from limited observations requires assumptions that cannot themselves be justified inductively without circularity. Hume's analysis created what Immanuel Kant later described as the crisis that awakened him from dogmatic slumber and prompted the critical philosophy. Yet Hume himself remained deeply impressed by the practical achievements and never intended to discredit the science entirely. He distinguished practical certainty sufficient for life and scientific investigation from absolute philosophical certainty that skepticism showed unattainable. The experimental method works effectively for prediction and explanation, even if its ultimate rational foundation remains philosophically obscure. We can reliably use induction while acknowledging honestly that we cannot fully justify its validity through philosophical arguments. This pragmatic response accepted human cognitive limitations while defending the legitimacy of empirical investigation against excessive skeptical demands. Continental philosophers engaged the Cambridge work differently than British empiricists, often emphasizing mathematical achievements over methodological claims. Voltaire became the greatest French popularizer during the 1730s and 1740s through his Elements of the Philosophy. The book presented the Principia and Optics to educated readers lacking advanced mathematical training through clear explanations and vivid examples. Voltaire championed the new science as exemplifying reason's power against religious superstition and philosophical dogmatism that had dominated European thought. Émilie du Châtelet produced the definitive French translation of the Principia that remains the standard reference today for non-English readers. She was a brilliant mathematician who deeply understood the work both technically and philosophically, with sophistication matching any contemporary. Her commentary clarified difficult passages and connected the physics to Leibnizian metaphysics in ways exploring how competing philosophical traditions might be synthesized. Du Châtelet showed possibilities for integrating insights from rival approaches rather than treating them as mutually exclusive alternatives. The Leibniz-Clarke correspondence of 1715 and 1716 played a crucial role in philosophical discussions that followed across decades. Leibniz criticized absolute space as violating the principle of sufficient reason that nothing happens without adequate explanation. If space exists absolutely, why would God place the material universe at one location rather than another in that undifferentiated space? There could be no sufficient reason for choosing one position over another, yet God acts only for sufficient reasons. Therefore, absolute space cannot exist as an independent entity prior to material relations constituting relative space. Samuel Clarke defended the Cambridge position, formulating connections between space, divine omnipresence, and providential action in systematic theology. The exchange ranged across physics, metaphysics, and theology, with neither side conceding their fundamental positions. Both recognized that deep questions about God's relation to creation were ultimately at stake beyond narrow technical disputes. This debate remained influential throughout the 18th century, shaping how thinkers across Europe understood the philosophical implications. The controversies defined intellectual battle lines between rationalist and empiricist approaches to knowledge and metaphysics. Kant's development in the 1770s centered on problems of space, time, and causation that the previous work had made philosophically urgent. He recognized that both rationalist metaphysics and empiricist skepticism faced fatal difficulties that neither could resolve satisfactorily. Rationalism claimed knowledge through pure reason, independent of experience, but could not explain how such knowledge applies to the empirical world. Empiricism grounded knowledge in experience, but could not explain how science achieves necessary and universal truths, transcending particular observations. Neither approach adequately explained how the mathematical physics achieves synthetic knowledge about nature that is both necessary and empirically applicable. Kant's critical philosophy attempted to transcend the rationalist-empiricist dichotomy through a revolutionary reorientation of epistemology and metaphysics. Space and time are neither objective features of things in themselves, nor merely empirical relations between perceived objects. Instead, they are pure forms of sensuous intuition that structure all possible experience prior to any particular empirical content. This makes them necessary for experience while not being properties of reality, independent of human cognitive faculties. Similarly, causation is not discovered empirically as Hume argued, nor derived from pure reason as rationalists claimed. Causation is a category that understanding necessarily imposes on experience to make objective knowledge possible at all. Without causal structure, experience would reduce to chaotic sensory flux without coherent order or law-governed regularity. The categories of understanding, including causation, substance, and interaction, are conditions for the possibility of experience itself. This transcendental argument explained how the science achieves necessity while remaining empirically applicable to phenomena. The laws hold with necessity because they reflect structures our minds must impose to have coherent experience, but they apply only to phenomena as they appear to us, not to things in themselves beyond possible experience. This limited the scope of legitimate knowledge while vindicating scientific method within its proper domain of empirical phenomena. Kant's reinterpretation dominated German philosophy throughout the 19th century, and separated physics from metaphysical commitments about absolute space. The mathematical laws could be preserved while rejecting theological interpretations of space as divine presence and time as divine duration. Physics became autonomous from metaphysics and theology, concerned only with phenomena and their mathematical relationships. This separation contributed to the emerging secular scientific worldview, where natural investigation proceeds independently of religious considerations. Meanwhile, practical science developed by extending methods to new domains throughout the 18th and 19th centuries. Lagrange and Laplace reformulated mechanics using analytical methods that replaced geometric demonstrations with algebraic equations. They achieved spectacular successes predicting planetary motions with unprecedented precision through improved mathematical techniques. Laplace famously claimed his celestial mechanics needed no hypothesis about God when Napoleon questioned the deity's absence from the work. This secularization completely inverted the original intentions where physics manifested divine action through mathematical laws describing God's governance. The Enlightenment appropriated the Cambridge natural philosopher as patron saint of rational secular inquiry, while suppressing theological dimensions. They highlighted mathematical physics and experimental methodology, while ignoring or remaining ignorant of theological and alchemical foundations actually motivating research. Each philosophical or scientific movement selectively appropriated useful elements, while rejecting aspects incompatible with their agendas and worldviews. Deists cited the work to argue for a God who created natural laws, then withdrew from active intervention in the world. Materialists used mechanical explanations to eliminate purpose and design from natural processes entirely. Empiricists invoked methodological principles against metaphysical speculation, while overlooking the metaphysical commitments pervading the actual work. None of these appropriations accurately represented the complex historical figure who unified physics, theology, and alchemy in coherent vision. The sanitized version that emerged bore little resemblance to the heretical theologian obsessed with biblical prophecy and alchemical transmutation. 19th century positivism made this mythological figure their intellectual ancestor, championing rejection of metaphysics in favour of mathematical description. Auguste Comte and his followers saw the history of thought progressing from theological through metaphysical to positive scientific stages. They placed the Cambridge achievements at the birth of the positive stage where mathematical laws replaced theological or metaphysical explanations. This was profoundly ironic given the actual theological commitments and metaphysical concerns pervading the work from beginning to end. The hypothesis non fingo declaration became a positivist slogan advocating mathematical description, without metaphysical interpretation or causal explanation, but the phrase originally targeted specific mechanical hypotheses like vortices, while preserving theological interpretation of gravity as divine action. Ripping it from context and using it against all metaphysics and theology completely reversed its intended meaning and function. The Enlightenment Newton was a fiction constructed for philosophical and ideological purposes rather than a historically accurate representation. Only 20th century scholarship recovering the hidden manuscripts revealed the actual complexity of the intellectual project and its motivations. Throughout all these philosophical appropriations and debates, certain core insights remained influential, even when specific doctrines were rejected. The conviction that nature operates according to mathematical laws expressible in equations became fundamental to modern science across all domains. The methodology combining mathematical rigor with empirical constraint through systematic testing defined the scientific method. The distinction between knowing that phenomena follow certain patterns and knowing why they do so shaped philosophy of science debates. The recognition that scientific theories might be reliable without being absolutely certain marked mature epistemology for empirical investigation. These methodological and philosophical contributions endured through revolutionary changes in physical theory that replaced specific doctrines with radically different frameworks. The system contained profound contradictions that remained unresolved throughout a lifetime of intellectual effort, and which later science would expose with increasing clarity. The methodological declarations emphasized deriving conclusions from phenomena without feigning hypotheses or inventing speculative mechanisms. Yet the fundamental framework relied on metaphysical entities like absolute space that could never be observed directly in any experiment. This gap between empirical rhetoric and rationalist practice troubled critics from the beginning, and generated philosophical debates continuing for centuries. The doctrine of absolute space proved necessary for the physics to function as originally formulated with precise mathematical laws. The laws of motion required distinguishing true acceleration from merely apparent changes in relative position between bodies. Without absolute motion defined relative to space itself, the second law becomes empirically empty since any motion exists only relative to some chosen reference frame. Different frames yield different descriptions of the same situation with no way to determine which description captures reality. Yet absolute space and time cannot be measured or observed directly through any experimental procedure available to investigators. We always perceive only relative motions and relative positions of observable material bodies in our vicinity. No measurement provides direct empirical access to the absolute magnitudes the theory requires as foundations for dynamical laws. The architect of the system openly acknowledged this difficulty in the Principia's scholium on space and time. We lack direct empirical access to absolute quantities and must infer them indirectly from phenomena through theory-mediated reasoning. Forces acting on bodies provide clues for distinguishing real from apparent accelerations according to the theoretical framework. True changes in motion occur only when forces act on bodies themselves, rather than merely on surrounding reference frames. But this response contains circular reasoning that troubled philosophers immediately. Defining forces already presupposes the distinction between real and apparent motion that forces are supposed to establish empirically. The bucket experiment aimed to demonstrate absolute rotation independently of surrounding material reference frames. When a bucket of water spins, the water surface becomes concave and rises up the sides due to centrifugal effects. This concavity persists even when water and bucket rotate together with no relative motion between them. Therefore, the concavity must reveal genuine rotation relative to space itself rather than relative to surrounding matter. But Ernst Mach criticized this reasoning in the late 19th century by proposing alternative interpretations compatible with relationism. Perhaps the water's shape responds to rotation relative to distant masses throughout the universe, rather than absolute space. If all the stars rotated around a stationary bucket, the same centrifugal effects might arise from that relative rotation. This possibility undermined claims that the bucket experiment provided empirical proof of absolute motion independent of material reference frames. Einstein's general relativity eventually vindicated Mach's intuition by showing that inertial effects depend on matter's distribution throughout space. Mass curves space-time, and this curvature locally determines inertial reference frames and what counts as accelerated motion. The distinction between inertial and non-inertial motion survives, but becomes dynamical rather than absolute as originally conceived. Space does not exist independently with fixed structure defining acceleration, but rather matter and energy determine space-time's geometry. The theory of gravitation faced the philosophical problem of action at a distance that continental critics emphasized relentlessly. How could the sun affect Earth across 93 million miles of empty vacuum without any intervening medium? Mechanical philosophy demanded that matter affects matter only through direct contact between bodies in physical proximity. Gravitational attraction across vacuum appeared to violate this principle by reintroducing occult qualities that modern philosophy aimed to eliminate. Gravity acting instantaneously across empty space seemed to resurrect Aristotelian substantial forms and sympathies that mechanical explanation had successfully banished. Leibniz and Huygens found it philosophically repugnant despite the mathematical theory's predictive accuracy and explanatory power. Continental natural philosophers struggled to accept action at a distance, even when the alternative vortex theories failed empirically. The response emphasized that demonstrating gravity's existence and mathematical law sufficed for natural philosophy without mechanical explanation. The theory had proven that gravity operates according to precise mathematical relationships, derived from careful observation of celestial motions. Whether gravity operates through unknown mechanisms or directly across space remained an open question for future investigation. Private speculation about ethers or subtle fluids that might mechanically transmit gravitational effects existed in unpublished manuscripts. But publishing such speculations would violate methodological principles by presenting unproven hypotheses as demonstrated conclusions. Better to acknowledge ignorance about mechanism than to invent explanations lacking experimental foundation and empirical support. This methodological stance was philosophically bold, but made the position vulnerable to charges of inconsistency from critics. The same person demanded mechanical explanations from others like Descartes and Leibniz, while exempting gravity from this requirement. Vortex theories at least offered mechanisms, even if details remained speculative and empirically inadequate. The alternative appeared to abandon completely the goal of genuine physical explanation in favour of mere mathematical description. Later, physics vindicated willingness to accept mathematically precise forces without mechanical reduction to contact action. Electromagnetic forces act across empty space without material medium in ways analogous to gravity's operation. Quantum field theory describes forces through mathematical equations rather than mechanical collisions between visualizable particles. The demand for mechanical explanation proved too restrictive for fundamental physics once investigation reached deeper levels. However, modern forces differ fundamentally from the original gravitational conception in ways that could not be anticipated. They propagate at finite speed rather than acting instantaneously across arbitrary distances regardless of separation. Changes in source masses require time to affect distant bodies, travelling at light speed through space-time structure. Instantaneous action at a distance violated not only philosophical preferences, but also empirical facts discovered through later investigation. The corpuscular theory of light illustrated another important limitation in the physics, despite its initial plausibility and explanatory success. Impressive arguments supported the view that light consists of material particles rather than waves propagating through media. Light travels in straight lines, creating sharp shadows, unlike sound which bends around obstacles through diffraction. Reflection resembles elastic collision of particles bouncing off surfaces at angles equal to their incident approach angles. Different colours might correspond to particles with different sizes or speeds, explaining their varying refractive properties. But the corpuscular theory could not adequately explain phenomena like colours in thin films that seem to require wave properties. Why does light sometimes reflect and sometimes transmit through soap bubbles, apparently at random without obvious differences in conditions? The proposal of fits alternately disposing corpuscles toward reflection or transmission was an awkward addition, grafting wave properties onto particle foundations. These fits required that corpuscles create waves in surrounding ether, which then overtake the corpuscles and modulate their behaviour periodically. This hybrid theory preserved corpuscular basics while incorporating wave elements, where phenomena absolutely demanded them through observations. Thomas Young's double-slit experiment in 1801 provided crushing evidence against pure corpuscular theory that could not be ignored. When light passes through two narrow slits, it produces interference patterns with alternating bright and dark bands on screens. These patterns unmistakably demonstrate wave behaviour through constructive and destructive interference of waves from both slits. Particles travelling through one slit or the other could not create such patterns without wave properties. Throughout the 19th century, additional experiments on interference, diffraction, and polarization overwhelmingly confirmed wave theory's superiority. Augustin Jean Fresnel developed comprehensive mathematical treatment, explaining optical phenomena that corpuscular approaches could not handle. By century's end, wave theory completely dominated optics, and the corpuscular approach seemed definitively refuted by evidence. Then quantum mechanics around 1900 unexpectedly resurrected particle concepts in radically transformed form through new discoveries. The photoelectric effect revealed that light ejects electrons from metals in ways wave theory could not explain properly. Electron energy depends on light's frequency rather than intensity, contradicting predictions from classical wave theory completely. Einstein proposed in 1905 that light consists of discrete energy packets called photons with energy proportional to frequency. Electrons absorb whole photons in quantum jumps, rather than accumulating energy gradually from continuous electromagnetic waves. Modern physics recognizes wave-particle duality as fundamental to quantum mechanics, rather than a paradox requiring resolution through choosing one view. Light displays wave behavior in interference and diffraction experiments, where wave properties become observable and measurable. It displays particle behavior and photoelectric effect and Compton scattering, where discrete quantum properties dominate observations. Neither classical waves nor classical particles describe quantum entities adequately, since they exhibit both aspects contextually. The corpuscular theory thus anticipated aspects of modern photon theory, despite incompleteness within classical physics frameworks. The intuition that light consists of discrete entities traversing space captured partial truth that pure wave theory missed. The dispute between corpuscular and wave theories could not be resolved within classical physics because both captured different complementary aspects. They described facets of quantum reality using inadequate classical concepts that proved insufficient for complete understanding. The methodology created tensions between inductive caution and theoretical boldness that never achieved complete reconciliation. Claims emphasized deriving conclusions from phenomena through induction without hypothetical speculation beyond observational warrant. Yet universal gravitation extended far beyond observational evidence through enormous theoretical extrapolation from limited data. The investigation examined only terrestrial objects and visible celestial bodies accessible from Earth's surface through available instruments. Extrapolating to all matter everywhere throughout infinite space involved massive theoretical leaps beyond strict empirical justification. Countless potential exceptions or limitations might exist beyond experimental access where different laws might operate. The third rule of reasoning justified this universalization by asserting that qualities found in all tested bodies apply universally, but this rule itself was not derived from phenomena, but rather was a methodological principle assumed to make natural philosophy possible. The justification for the rule could not come from induction without begging the question about induction's validity. David Hume's critique of induction systematically exposed this vulnerability at the heart of the experimental method's foundations. No amount of observed constant conjunctions proves that future cases must resemble past patterns already witnessed repeatedly. We cannot inductively demonstrate that induction works without circular reasoning that assumes induction's validity in the argument. Confidence in generalizations based on limited observations lacked the certainty claimed for conclusions supposedly derived rigorously from phenomena. The problem of induction remains philosophically unresolved despite practical scientific success that continues unabated to this day. We use inductive inference because it works, effectively for prediction and technological application, despite lacking rational justification. The methodology achieved spectacular practical success, but its logical foundations remained philosophically insecure and vulnerable to skeptical challenge. This gap between practical achievement and philosophical justification persists in modern science across all empirical disciplines. The theological framework also created contradictions with the public natural philosophy that were never fully resolved or integrated. Private belief held that God continuously acts in the world, maintaining cosmic order through ongoing providential intervention. Yet published physics treated nature as governed by mathematical laws, operating mechanically according to deterministic principles. How divine action relates to natural law remained unclear, and generated tensions throughout the entire intellectual system. If God must periodically adjust planetary orbits to maintain stability, then natural laws alone prove insufficient for cosmic order. This suggests creation is imperfect and requires divine correction, as Leibniz charged in their famous correspondence through intermediaries. But if laws govern completely without need for intervention, then God's role reduces to initial creation, as deists argued. The goal was active divine governance without undermining natural law's autonomy, but achieving this balance proved difficult. The heretical theology created additional complications that had to remain concealed from public view to avoid persecution. Theological claims in the general scholium carried Arian subtext noticeable only to readers familiar with Trinitarian controversies. The work simultaneously made physics accessible to everyone while encoding heterodox theology for initiated readers who understood. This double coding reflected an intolerable position between intellectual honesty and survival necessity that imposed psychological burdens. The removal of theological and alchemical manuscripts after death in 1727 distorted the legacy for generations of scholars. Enlightenment thinkers praised a rational, mechanistic, natural philosopher who never actually existed in historical reality. The real figure spent more time on theology and alchemy than physics, treating them as unified investigation of divine action. Understanding the complete intellectual project requires recognizing how seemingly disparate pursuits formed a coherent, unified vision in one extraordinary mind. Modern disciplinary boundaries between physics, theology, alchemy, and historical scholarship did not exist for this thinker, as they would emerge later. All these investigations aimed at a single ultimate goal, revealing the nature and will of God through creation study. Natural philosophy, biblical exegesis, and alchemical experimentation were different methods pursuing the same fundamental truth about divine reality and human existence. The conviction held that God left traces of divine wisdom in multiple books, requiring different interpretive methods for proper reading. The Book of Nature reveals God's power and intelligence through mathematical laws and orderly phenomena observable to anyone. The Book of Scripture reveals God's will and plan for humanity through prophetic and historical texts requiring careful philological analysis. Ancient philosophical and alchemical texts preserve distorted fragments of original revelation that critical study could restore. All three sources ultimately converge toward identical truths when properly interpreted, purified of corrupting additions and understood completely. This convergence was not hoped for possibility, but confident expectation grounded in theological conviction about divine revelation's unity. Natural philosophy discovers mathematical laws governing motion and force throughout the cosmos at every scale of investigation. Theology restores pure monotheism, underlying corrupted Trinitarian doctrines developed centuries after Christ's apostles taught simple truths. Alchemy reveals active principles governing matter's transformations beyond what mechanical interactions alone could possibly explain. The Prisca Theologia framework unified these domains by showing they all derive from primordial divine revelation to earliest humanity. God revealed both natural and moral truths to Noah and the patriarchs, who transmitted wisdom to their descendants. Ancient peoples preserved this knowledge through various cultural traditions that maintained it imperfectly across generations and geography. The task confronting later investigators was restoring and purifying these traditions to recover original, unified knowledge about nature and divinity. Every discovery in physics revealed God's methods of acting in creation, contributing to proper understanding of divine nature. Every correction to chronology clarified Scripture's prophetic timeline, showing how history unfolds according to predetermined divine plan. Every theological manuscript arguing against Trinitarian corruption defended original apostolic Christianity against accumulated institutional errors and distortions. These were not separate intellectual projects pursued independently, but aspects of one comprehensive sacred mission, transcending mere academic curiosity, the anti-Trinitarian. Theology was not incidental, but absolutely central to the entire vision and its animating purpose. The Trinity represented the same kind of corruption that infected natural philosophy during medieval decline into scholastic Aristotelianism. Just as elaborate metaphysical systems obscured nature's mathematical simplicity, Trinitarian formulations obscured God's absolute unity and simplicity. Both required reformation through return to original sources purified of later additions imposed by corrupted authorities. The parallel between theological and scientific reformation was not metaphorical, but literal in the thinker's self-understanding and motivation. Athanasius corrupted Christianity in the 4th century the same way scholastics corrupted natural philosophy in medieval universities. Both distortions needed correction through critical study of ancient texts and willingness to question received authority from tradition. The concept of absolutely unified and omnipresent God fundamentally shaped the physics in ways modern readers often miss. Divine omnipresence means God exists everywhere simultaneously, literally constituting space itself through eternal ubiquitous presence everywhere. Duration and space are modes of God's existence rather than independent containers housing divinity from outside its essence. This makes space quasi-divine rather than purely physical reality, explaining why everything including minds must relate somehow to space. To exist means to exist somewhere even for spiritual beings and God himself, making spaceless existence equivalent to non-existence. The unity and continuity of space reflect God's indivisible unity that Trinitarian theology wrongly multiplies into 3 persons. Similarly, absolute time's uniform flow represents God's eternal duration, ordering all events in creation from beginning to end. Past, present, and future exist simultaneously for God, in eternal present transcending temporal succession we creatures experience. But creation perceives time as irreversible flow of moments from earlier to later states according to causal determination. Absolute time provides the framework within which all changes and motions occur according to divinely ordained mathematical laws. Gravity itself might be direct divine action rather than mechanical force transmitted through material medium filling space. God's will maintains the cosmos by creating attractive forces between all material bodies everywhere throughout infinite space. The mathematical inverse square law describes how God chooses to govern planetary motion and terrestrial falling objects identically. Natural law is divine will manifesting through regular predictable action, rather than arbitrary miraculous interventions breaking patterns. This gave the physics an actively theistic character completely opposite to deistic or materialistic interpretations later appropriators imposed. God does not merely create initial conditions, then withdraw, but continuously sustains every aspect of natural order presently. The conviction that physics reveals divine action made investigation a form of worship and religious duty rather than secular inquiry. Alchemy searched for active principles, complementing inadequate mechanical philosophy that treated matter as purely passive and inert. Pure mechanism explaining everything through size, shape, and motion alone could not account for chemical selectivity and vital processes. But matter imbued with active principles directing specific combinations could accomplish what mindless mechanism could never produce. These principles might be God's continuous creative activity, operating at microscopic scales, invisible to unaided observation and measurement. The philosopher's stone represented matter in maximally active, perfected state, embodying divine virtue most completely in material form. Transmutation became possible through transferring these active principles to base metals, transforming their essential natures through natural process. This was not magic or supernatural intervention, but natural philosophy extended into domains where mechanical explanations obviously failed. Alchemical investigation explored aspects of divine action in matter that mathematical equations could not capture or express adequately. Both aimed at revealing how God works in creation, using different methods appropriate to different phenomena and scales. The study of biblical prophecy aimed to decode God's predetermined plan for human history's development across millennia. Daniel and Revelation encrypted information about kingdoms rising and falling, religion's corruption and eventual restoration before end times. Elaborate interpretive principles matched prophetic symbols to historical realities, with specific dates and events corresponding to encoded predictions. The corruption began when Charlemagne was crowned in 800, establishing the system dominating Europe for over a millennium. Restoration would occur around 2060, giving 1260 years for the prophesied apostasy to run its course. Living during this corruption meant preparing for eventual restoration by recovering authentic wisdom lost during decline and distortion. Natural philosophical work and theological research both contributed to this preparation by establishing truths future generations would desperately need. The emotional and spiritual investment in recovering ancient wisdom exceeded even the formidable intellectual challenges involved in the research. This was not merely academic curiosity about historical questions, but sacred mission preparing for God's eventual restoration of true religion. Science and theology participated in God's providential plan for revealing truth to humanity across historical development toward final consummation. Methodological unity underlay all these diverse investigations, focusing on careful observation and rigorous textual criticism across domains. The same empirical methods examined prismatic light refraction, studied manuscript variants, and recorded chemical transformations systematically. Critical evaluation of evidence, systematic comparison of sources, and cautious inference from data governed natural philosophy and biblical scholarship equally. The intellectual virtues of precision, honesty, and skepticism toward authority applied universally regardless of subject matter under investigation. Experimental approaches in physics extended to theological method treating scripture as observational data, requiring critical analysis and interpretation. Comparing manuscript variants and noting discrepancies paralleled the natural historian's classification of specimens according to observable characteristics. Textual criticism identified corrupting interpolations by separating genuine revelation from human additions inserted over centuries. This empirical approach to theology offended those treating scripture as uniformly divinely inspired without human corruption or error. The alchemical investigations involved systematic experimentation, recording results, and adjusting procedures based on observed outcomes and patterns. Alchemical authorities were not accepted uncritically, but tested through laboratory work attempting to replicate claimed transformations. This experimental approach unified methodology across fields where others saw fundamentally different kinds of inquiry requiring separate standards. Knowledge always required empirical grounding regardless of whether studying light, scripture, or chemical transformations in laboratory furnaces. Mathematics also unified different investigations, though less obviously than the experimental method common to all domains. Natural philosophy explicitly used mathematics in laws of motion, and gravitational theory expressed through geometric demonstrations. But chronology also employed mathematical calculations determining dates from astronomical data mentioned in ancient texts. Even prophetic interpretation involved numerical patterns and temporal calculations using the day-year principle and symbolic numbers. The conviction that mathematics reflects divine rationality, ordering creation, extended to all domains of investigation without exception. Mathematical harmonies in planetary motion reveal God's aesthetic perfection, and rational design governing celestial mechanics universally. Ancient sages like Pythagoras understood this mathematical character of reality, explaining their emphasis on number and proportion. The unity explained exceptional motivation and productivity across such diverse, technically demanding fields, requiring different specialized skills. This was not dabbling superficially in unrelated hobbies, but total dedication toward one comprehensive goal, transcending narrow specialization. Each investigation contributed to understanding God's nature and recovering primordial revelation corrupted over centuries of decline. This gave the work existential urgency and personal meaning far exceeding mere intellectual curiosity about nature's workings. It also explained secrecy surrounding most work, since premature disclosure could destroy ability to continue the sacred mission. Revealing heretical theology would bring professional ruin, making further investigation impossible under institutional and legal constraints. Publishing incomplete alchemical speculations would expose sacred knowledge to corruption or ridicule by unprepared audiences incapable of understanding. The practice of concealing important ideas reflected ancient mystery religion models, protecting truth through graduated disclosure to initiates. Profound truths should not be cast before those unprepared to receive them properly or likely to misuse knowledge. The Pythagorean style of encoding deeper meanings in seemingly simple statements became a deliberate rhetorical and compositional strategy. Published works contained multiple levels of meaning accessible to different audiences according to their preparation and spiritual maturity. Ordinary readers found mathematical proofs and experimental descriptions sufficient for practical application and technological development. Initiated readers recognized theological subtexts and connections to ancient wisdom traditions that surface meanings concealed from casual observers. The deepest levels remained accessible only to those grasping anti-Trinitarian implications and unified vision connecting all investigations. The tragedy is that this unified vision could not survive death in 1727 with integrity intact. Executors suppressed theological and alchemical manuscripts, protecting reputation, but distorting understanding for subsequent generations of interpreters. The Enlightenment appropriated a sanitized rationalist who bore little resemblance to the actual historical figure's complexity and motivations. They celebrated mathematical physics and experimental methodology, while ignoring theological foundations that actually drove the research from beginning to end. Modern scholarship painstakingly reconstructed the unified vision from manuscript evidence recovered through 20th century auction sales and archives. We now understand that physics, theology, and alchemy constituted one integrated intellectual system, rather than separate compartmentalized interests. This recognition transforms interpretation of published works by revealing previously hidden dimensions and meanings throughout the texts. Theological propositions in the general scholium are not afterthoughts, but express foundational convictions underlying the entire Principia's arguments. Yet we cannot fully recover the original perspective because our intellectual world differs fundamentally from 17th century assumptions. We presume science and religion occupy separate non-overlapping domains with different methods and truth claims keeping them distinct. We distinguish sharply between empirical investigation and metaphysical speculation in ways the earlier period did not recognize. Our disciplinary divisions prevent seeing connections that seemed obvious to someone operating before those boundaries crystallized. The unified vision also contained serious tensions and contradictions that could not be fully resolved within available frameworks. How divine action relates to natural law remained conceptually problematic, despite various attempts at reconciliation and synthesis. Whether matter possesses intrinsic active principles or depends entirely on divine will was never clarified to complete satisfaction. The relationship between mathematical description and physical explanation generated persistent confusion throughout the work and subsequent reception. These contradictions proved productive by forcing later thinkers to address fundamental questions about scientific explanation and its limits. Does physics aim to describe nature's behaviour mathematically, or explain why nature behaves in observed ways necessarily? Can empirical science separate from metaphysical commitments about reality's ultimate nature and structure, or do they remain inseparably connected? The work raised these questions unavoidably, demanding philosophical clarification that continues generating debate among philosophers of science today. The legacy shapes both scientific practice and philosophical reflection on how we understand investigation's nature and proper methods. Mathematical physics became the model for all exact science, across domains from chemistry to biology to social sciences, but philosophical contradictions revealed by the work continue provoking arguments about scientific method, realism, and explanation's nature. We still grapple with problems the original investigations identified even after rejecting the specific solutions proposed initially. Understanding the complete figure requires embracing contradictions rather than resolving them artificially through selective emphasis on some aspects. Someone was simultaneously the founder of mathematical physics and an obsessive biblical scholar questioning core Christian doctrines fundamentally. An alchemical experimenter searching for active principles in matter, and a rigorous mathematician demanding empirical foundations for theories. A believer in ancient wisdom needing recovery, and an innovative thinker creating genuinely new frameworks unprecedented in scope. These tensions were not failures to achieve consistency, but reflected the intellectual situation's genuine complexity and ambiguity. The mind synthesizing multiple traditions and methods into novel combinations necessarily embodied contradictions those traditions contained. The unified vision brought together elements that subsequent specialization would separate into incompatible domains and methodologies. Modern physics confirmed some intuitions while rejecting others, vindicating aspects of the vision in unexpected, transformed ways. Transmutation became possible through nuclear reactions, though not via philosopher's stone or chemical processes as originally imagined. Chemical reactions involve forces between atoms, though not purely mechanical collisions that Cartesian philosophy exclusively recognized. Space-time structure is dynamical and curved by matter, though not absolute space, as originally conceived in theological terms. Quantum mechanics reveals wave-particle duality transcending classical concepts that disputants employed in their bitter 17th century controversies. Each revolutionary transformation preserved elements while radically reconceptualizing frameworks in ways inconceivable to original participants in debates. The enduring influence stems from raising questions that remain urgent even after specific answers proved inadequate or mistaken. How does mathematics relate to physical reality? And why does mathematical description work so remarkably well for prediction? What distinguishes legitimate scientific explanation from mere description? Or are they ultimately the same thing after all? Can we ground physical laws in deeper principles? Or must we accept some regularities as brute facts requiring no further explanation? These questions emerged unavoidably from the work and continue animating philosophy of science despite radical theory changes across centuries. The figure who saw connections others missed created frameworks that subsequent generations refined, rejected, and revolutionized repeatedly. Yet something essential persists through all these transformations: the conviction that nature operates according to mathematical principles, discoverable through systematic investigation. That empirical observation must constrain theoretical speculation rather than allowing unbounded system building detached from phenomena entirely. That apparent diversity of phenomena might reduce to underlying unity once we discover the right mathematical and conceptual tools. These core insights survive even as specific theories come and go with scientific progress and accumulated observational evidence. The unified vision ultimately failed because it attempted to synthesize elements, that would prove incompatible once investigation advanced further. Science and theology separated into autonomous domains with different methods and standards appropriate to their distinct subject matters. Physics became mathematical and empirical, while theology remained interpretive and normative without direct empirical testing of claims. Alchemy split into chemistry as a legitimate science and discredited transmutation as impossible within chemical frameworks available. The Prisca Theologia framework was abandoned as historical scholarship developed more sophisticated methods for studying ancient texts and cultures. Each separation was necessary for progress in the respective domains, but something was lost when the unified vision fragmented completely. The sense that investigating nature reveals something about ultimate reality and our place in the cosmos mostly disappeared from science. Physics became instrumentalist, concerned with prediction and control rather than metaphysical truth about reality's fundamental nature beyond phenomena. The questions about meaning, purpose, and divine action that animated the original work became illegitimate within scientific discourse entirely. Whether this separation represents progress or impoverishment remains debated, with no consensus emerging across philosophical and scientific communities. Some argue that purifying science of metaphysics and theology enabled spectacular advances impossible under earlier integrated frameworks constraining inquiry. Others contend that losing the sense of investigating reality's ultimate nature impoverishes science, reducing it to mere technique. The historical figure stands at the transition between these worldviews, embodying both the medieval integration and modern separation simultaneously. Understanding requires appreciating both the power of the unified vision and the reasons it ultimately could not survive intact. The achievement was creating mathematical physics as a discipline with rigorous methods and spectacular predictive success across vast domains. The limitation was embedding this achievement within theological and alchemical frameworks that subsequent investigation would reject or transform beyond recognition. Both dimensions remain essential for grasping what was actually accomplished and what it meant to the person who accomplished it. The sanitized Enlightenment version that stripped away theology and alchemy was a fiction, but so would be ignoring the mathematical physics. The complete truth lies in the paradoxical combination: someone who was both a rigorous mathematical physicist and a heretical theologian, both an empirical experimenter and an alchemical mystic seeking ancient wisdom, both a revolutionary innovator and a conservative restorer of corrupted traditions. These contradictions cannot be resolved but must be held in tension to understand the unified vision that transformed human understanding of nature forever, despite its ultimate fragmentation into separate domains.